Check 1, 2, 3, 4, 5, 6, 7, 8.
Hello. Welcome to this John Deere Machine Learning Symposium. Most of you are watching online. Good morning to those who are here, and greetings from Northern Iowa to those who are watching online. So it's time for us to start, and I would request Professor Douglas Mupasiri, the head of the mathematics department, to make opening remarks. Doug?
Good morning to those of you who are here at the University of Northern Iowa, and good morning also to those of you who are watching or viewing this event from outside of our campus. I am particularly thrilled to have to welcome a number of people who are joining us from abroad. This is great that we are able to host an event of this type and to have folks from all over the world joining us for the event. I want to begin by thanking, obviously, the John Deere Company for sponsoring this event. We could not have done it without their help. There is a committee that was involved in organizing the program for this symposium, and I want to begin by thanking the members of that committee. First, I want to thank Professor Syed Kimani, who just spoke a moment ago. He really is sort of the person who got this whole thing going from the very beginning. So I owe a special debt of gratitude to Professor Kimani for making this happen. I also am particularly keen to mention that many of the folks who are joining this event today learned about it personally from Dr. Kimani. So I really want to put a shout out there for the work that he's put into this. Joining him on the program committee were Dean Ejaz Ahmad, who is at Brock University in Canada, Emily Bizenius, Senior Data Analyst at Elevate. Emily, a special shout out to you. You're one of our graduates, so I'm thrilled that you were able to help with this work. And also helping as a member of that committee was Dr. Zheng Wei Hu, who will also be speaking here, and he is actually a John Deere employee, a John Deere scientist. So we're grateful to him for that. And joining this group of people I just mentioned was a local committee here, and leading that local committee was again Professor Kimani and Rick Seeley. Rick Seeley is the Director of IT, Media, and Technology Sciences at the University of Northern Iowa. And Rick and his team are the people that are making this whole event possible. So we owe a special debt of gratitude to them, and I wanted to extend my deepest thanks to them. Also helping on the committee locally is Dr. Doug Shaw. Professor Shaw is professor of mathematics here at the University of Northern Iowa. And helping also on the committee was Professor Maria Smodi, also a professor in the Department of Mathematics here at the University of Northern Iowa. And last but not least is the sort of unsung heroine of this event, Cindy Helgeson, who is our department secretary, spent hours and hours of work trying to make this event happen. And Cindy, we owe a great debt of gratitude to you for all the work that you've put into this. And I would be remiss if I did not mention Hilary Oberle, who is the Assistant Vice President for Strategy, Communications, here at, I'm in the University Advancement Office here at the University of Northern Iowa. It was Hilary who first approached Professor Kimani and asked him if he had an idea that she could take to the folks at John Deere, and Professor Kimani, as he's always keen to do, had a brilliant idea of doing something like this. My hope is that this is the sort of event that we can have more of in the future. It would be great if we could do an annual event of this type. And so I am deeply, deeply grateful to all the folks who helped organize this, this event. I will now call Professor Kimani back to introduce our first speaker. Thank you so much. Thank you for joining us, and I hope you have a great day today. You know, we are all here to learn about, I guess, machine learning. So let the machines do their thing. Thank you.
Thank you, Doug. It's time to begin now with the presentations. And I'm really pleased that, and not a majority, but a large number of people who registered for this conference are students. Students from various countries, actually from 25 countries. And one of the biggest group of students is from Linköping University in Sweden, followed by big groups of students from India, the IITs in India, and also from Iran. I'm pleased that my old universities, Aligarh Muslim University, India, Isfahan University, Iran, and of course Shiraz University, Iran, they are all represented. So our first speaker is Professor Ridesh Rajan. He's a distinguished computer scientist. He has established himself as a front-rank research worker, and he is currently the department head, department chair at Iowa State University. Professor Rajan has pretty diverse interest in computer science, including including programming languages and software engineering, just two of his interests. Now, he is very much concerned with what he calls decreasing the barrier to entry to the barrier to entry to data science, data-driven sciences to broaden participation. It's a noble goal, and I believe he's succeeding very well. So I would not take more time. I would just request Professor Rajan to come and make his presentation on dependable data-driven discovery framework. Machine learning does not fly without dependable data. Professor Rajan.
Thank you, Saeed, Doug, organizers of this wonderful symposium. Thank you, John Deere, for supporting this, this wonderful event. So today's talk is about how to make data-driven decisions and discovery more trustworthy. Now you might say, okay, why should we worry about that? I am going to argue through a set of examples today that data-driven systems are becoming a critical part of all of our lives. They're becoming critical part of the social fabric. They have the capacity to influence decisions in very negative ways if one doesn't think about them very carefully. In my talk today, I will also give you a framework to think about dependability of data-driven systems. It's a framework that I will describe, and I will show some examples of how that framework can be applied. So let me begin with the reason why we should care about dependability in data-driven systems. And you know, most of us today probably used a map app to get here, right? And the map app usually shows red spots where there might be congestion, right? And that congestion is computed using sensing data from a variety of phones. Well, if there is a congestion shown on map, but you don't actually find the congestion, you know, nothing is wrong, nothing goes wrong. So far, so good. But if there is an autonomous vehicle that is driving on the street, and it predicts using data that the street is clear, and it turns out to be there is a pedestrian on the street, things go wrong. Similarly, if there is a medical analysis being done where the image is being analyzed to understand impact, whether that image shows there are certain tumor, and if the analysis comes back and says there's nothing wrong, there's no tumor, and there actually is a tumor, something does go wrong. People pass from these. Similarly, you know, if a plane is flying and it has a sensory control, it has sensors that check whether there are neighboring things that it has to avoid, and that data-driven decision system ends up saying that there's nothing around it, and there actually is something around it. Some major things go wrong. So what I'm trying to argue here is that while a number of uses of data-driven decision systems today are in circumstances that are will not be considered safety critical, there is plenty of examples today, plenty of use cases today where data-driven systems are being used to make decisions that are safety critical. Here are some other examples, you know, recommendation systems, monitoring systems, home control systems. So you want to know if a thief is around your house, you want to know it reliably, so to speak. If a data-driven decision system is being used to determine who is going to get admission into a college, who is going to get credit card, how much their credit is going to be, you want to make sure that that system can be depended upon, relied upon. If the data-driven system is being used to determine which person is going to get the interview and which person is not, you want to make sure that that system can be relied upon. So what happens if something goes wrong? Right? We talked about these systems. What happens if something goes wrong? So I will run you through some recent newsworthy stories on this. These are some publicly available examples of failure to understand the impact that failure of data-driven decisions can have on our society. So here are two examples of unfairness. Right? So the example, recruiting example, in this particular example, a data-driven system was being utilized to decide who to interview. And that system systematically picked male candidates to interview and systematically discarded female candidates from being interviewed. And it was found out, after much debate, that this was what was going on. Data-driven systems often are used to assign labels that are used for consumption by downstream systems. And this is a very, very famous example of where things that went horribly wrong. Accountability is another major concern. For instance, one very widely publicized chatbot made data-driven decisions to determine how to respond to questions. And due to the problem with ingested data, this chatbot quickly started to produce responses that were inappropriate and that were offensive. Data-driven systems were used to determine whether a certain aircraft is fit for flying, and failures were ignored as outliers, which didn't really lead to very positive result on the society, because people actually died as a result of failure. Uncertainty is another major concern. For example, data-driven systems are often used in autonomous vehicles to make hundreds of decisions about real-world objects. These systems are generally not 100% certain about these decisions. So one of the widely publicized cases was where there was a deadly crash, and there was another case where the pedestrian was not identified, and then led to the passing of the pedestrian. On top of these concerns, transparency has become a major issue. The behavior of the data-driven system cannot be fully understood. Some components of these systems can essentially act as black boxes that are not even understood by their creators fully. And that's not really a very, very good place for us to be. These concerns and others are compromising the credibility of data-driven decisions in a very, very big way. And that is bad because it undermines the trust of the society on fact-based decisions. A society can act appropriately if it continues to trust fact-based decisions. And if trust in fact-based decisions is compromised, the society as a whole may not be better off. In some cases, key members of the society are already abandoning the use of data-driven systems. For example, this Los Angeles Police Department that used data-driven programs to detect criminal activity has had some success in reducing crime rate. But when it found out that the use of the program and the decisions made by the program were unfair, it had to abandon that that program. So when it abandoned the program, of course, the benefits given by the software was also lost. So if one is not careful about whether we can depend upon data-driven decisions, one has the benefit of also throw the baby with the bathwater, so to speak. So I believe, and my colleagues believe, that a foundational research is essential to ensure that data-driven discovery and decisions are trustworthy. If we were to maintain public trust in data-driven decision, fact-based decision-making is critical to the vitality of the society. So this is a really, really important goal that we have in front of us. So let me explain a little bit about what we mean by dependable. Earlier I was having a discussion with Saeed about it. So we believe that the processes that produce those decisions need to be examined for dependability. That is, if the data science lifecycle, which is the process that used to produce decisions, that produces these decisions are dependable, then the decision that's coming out of it can be trusted upon by construction. So let's now define these two terms. What is a data science lifecycle, and what do we mean by dependable? And so this definition is shaped by my colleagues who have been working on this ISU Dependable Data-Driven Discovery Initiative since 2017. These are experts across a range of areas: computer science, programming language, software engineering, for methods, statistics, mathematics, application areas, and so on. And these opinions have been informed by discussions with these colleagues. So before we get into the data science life cycle, let's first think a little bit about what are the different types of data science life cycles. And here are three. One on the left would be a machine learning process that essentially what it does is it builds, we are just focusing on building predictive models. We are building predictive models using novel state-of-the-art artificial intelligence algorithms. Then the one in the middle will be the data engineering processes. There the goal is to manage and analyze large amount of data. And this is really focusing more on getting value out of data. And then there are team processes. So this is a collection of scientists coming together to work on data-related projects. So these are the life cycles are manifest itself in three different ways. In predictive way, in data mangling, and also in the human process that is used to make decisions. So here is a representation of this life cycle. This representation, we are concerned about different stages of the life cycle. For example, problem identification, as you can see here, is where typically we start. What is the problem that we want to solve? Then we want to understand how we're going to go about creating a study that's going to solve the problem. What data will be acquired? How will the experiment be set up? Acquiring data, cleaning data, and so on. Then we will go about doing some exploratory analysis over data. We want to understand the data a little bit better. If the life cycle involves predictive phases, then we'll typically do some sort of feature engineering to understand, which of the features of the data are important, which are not important. And usually these things will go back and forth until we have a good understanding. We would also then typically move to the modeling and training phase, do some sort of evaluation of the model, do prediction using that model. And now there are cases where the prediction immediately is applied. So for example, you take if a system, a data-driven system predicts that the car should turn left, there's an actuator which interprets that decision, and car turns left. So that's what interpretation is about. But there are also some times where a data scientist has to get up in front of the managers and give a presentation about what they found, right? So that's where the data scientist has to interpret what that data means, and then maybe communicate with the stakeholders about how they're going to act on that, how they might be able to act on that. And then a decision is made to what to do. So if in case of a car, for example, it's a decision to turn, and in case of a policy decision, it's a decision by policymaker to act on the data to what to do with it. And then there is an action. Something happens in the world as a result of that decision, and then we go back again to the. So this is typically how one goes about it. This is not meant to be exclusive to cyber physical systems. This is meant to be a representation that covers cyber physical human systems. So we are looking at it. We are looking at systems that can entail both a cyber component, physical component, and human component. Now, there are arrows, and I will talk a little bit about these arrows and what boxes means and so on. So here are a couple of definitions. So stage, in this presentation, when I use the word stage, it means a data science process. For example, problem identification, study design, acquisition. Edges are flow of data. So you are looking at it. There's data flowing from acquisition to exploratory data analysis and so on and so forth. It's not controlling. So one doesn't, data acquisition doesn't control what happens in exploratory data analysis. It's just, one thinks of these as, you can think of these as independently running things, independently executing things, which allows this representation to model a variety of circumstances. So the idea here is that we want to take a holistic approach to dependability of these systems beyond just thinking about the machine learning algorithm. So we got to think about what goes around the machine learning algorithm, because that part is really, really very important as well. If the processes early in the life cycle are not trustworthy, then it is unlikely that the whole thing is going to be trustworthy. It's not just this modeling and training piece that we have to worry about. So let me now get into the details of the parts of the framework. There are three major parts, three pieces: risks, measures, and mechanisms. Okay. The entire framework could be thought of as parameterized by different kinds of risks. For example, fairness is a risk, uncertainty is another kind of risk, complexity is another kind of risk, robustness, freshness, etc. So what is a risk? A risk is a cause that can lead to failures. Right? So uncertainty could lead to system making wrong decision. Fairness could lead to system treating people differently. A measure is a facet that serves to quantify the risk, and that also serves to provide tolerance levels. So you not just want to understand how to measure the risk, but you also want to understand how much risk can be tolerated, and how much risk, when do we exceed the tolerance level. So that's a very important part of the story. And mechanisms are additives to stages. So what you want, if you find a problem, what do you add to various stages to ensure that risks go back within the tolerance levels? Because that's essentially so this is kind of a high-level way of thinking about this issue. So identify the risk, figure out what metrics you're going to use to measure them, and what are the tolerance level for those metrics. And then if you end up determining that your risks are going to be outside the tolerance level, then you figure out a way to add something to stages so that they will back be within the tolerance level. So let me take a minute here and see if you have any questions from the audience. Yes?
So earlier you alluded to dependable systems.
Yep.
You brought up some questions about fairness as well.
Yep.
So how do you distinguish this? In your notion, are fair systems different than dependable systems? Do you see fairness as a component of dependability?
I think
Okay.
so fairness will be so just to repeat the question. The question was, fairness was brought up as an example. What role does fairness play in this framework? So fairness would be an example of a risk. So you would think of fairness as an example of a risk. And I will actually have fairness as an example here, because this is something we have worked on. So fairness would be considered as an example of a risk. And ways to measure fairness, like individual fairness and group fairness, would be considered metrics. And then you want the individual fairness and group fairness to be within certain tolerance level. So no, that's a great question. Thank you. Anyone else? Any other question? Yes.
Check. Okay, we have a question from online. This is Dale Lehman, and he says, what does Dr. Rajan think about data-driven decisions that, while imperfect, may be better than the human decisions they might replace?
They are certainly welcome. I think this is, the question is, we need to know the imperfection. We need to quantify the imperfection. I think that's, while we may have a decision that performs better than the human system, in order for a data-driven decisions to be trusted by society, one has to offer a credible proof, so to speak, as to why they're doing what they're doing and what are the limits under which they will not do what they're supposed to do. If there is a follow-up.
This is a separate question.
Yep, go ahead, please.
Okay, how does adding model interpredictability fit into your workflow and also mitigate risks?
Model interpretability. So model interpretability would be an example of a mechanism that one would add to the modeling and training, model evaluation step. So it's an example of a mechanism under this framework. Okay. If there are no more questions, I will probably I'll proceed. So we have thought about this framework at different levels of abstraction. So the lowest level of abstraction is the software code. You can think of this framework in the software code, and because that's what is implementing these data-driven decisions. You can think of them at the level of models of life cycle, abstract models, generally graph-based, and you can think of them at the level of algorithms. You can just study a single algorithm and say, okay, what's happening in the algorithm. So when you apply this framework at the highest level of abstraction, of course, it's more declarative, more richer properties can be analyzed and then reused. When you apply at the lowest level, this is closest to the actual functionality of the system. What you find is actually what's happening there. And at the model level, you abstract some of the details. Of course, you abstract some of the details from the code, but of course, you might be able to scale your application of the framework to larger systems and may be able to reason at a level that is more manageable. So a lot of times, what ends up happening is that you can take the software code and you get a model of the software code, and then some humans reason about the algorithm, human experts reason about the algorithm to create some knowledge for the model, and then you focus most of the application on this middle models level. Okay. So I'll show you an example of how this works out. And so in this example, the risk that we are going to be talking about is uncertainty. And the example that we're going to be using is the TSA system. So I'm assuming that most of us here have been to the airport, right? This is a system that the goal is that as you are going through the TSA system, it's scanning your body, looking at various parts of your body, and is determining whether you should go or whether you should be pulled aside for extra screening. Okay? And the goal is to decrease the false alarm so that the line can keep progressing. If everybody is pulled aside for extra screening, you can imagine most people missing their flights. And so the details are slightly smaller, but the way this works is that you have the system classifies things into low risk, unknown risk, high risk, and highest risk. And low risk people just get to fly using TSA pre. The unknown risk essentially get extra screening, and the high risk get a little bit more screening in a separate area, and then the highest risk essentially go somewhere else, so to speak. So not to get too much into the details, but one implementation of this algorithm uses a deep neural network to implement this process. And so the way that our framework would work in this setting is that from the code that is being utilized, in this case, this is building an LSTM model. You don't have to worry about what LSTM model is for the purpose of this talk. But it's the software code is implementing a model. And from this model, you would extract a graph that is a representation of the life cycle. And then in this graph, you will have nodes that corresponds to computation that happens here, that manipulates data, and then edges are flow of data between nodes. So my students have gone on into extracting this life cycle from the code for one implementation of this system. And so this is kind of what the model looks like, right? So you get the image of the person, and that image goes to a ResNet classifier, and through a variety of nodes, it eventually gives you the probability, and this P1 to P17 are probability of different parts of the body needing further scanning. Okay. So for this system, what is a risk? And what are the measures? So the risk is uncertainty, right? That you are uncertain whether certain parts of the body might hide something dangerous, right? So the next question is, how do you measure it? That's the second part. And so measure usually is the log loss of the in this particular system. Okay. So once you have these risks and notion of risk and measures, what can you do with it? So part of my group focuses on verifying whether the system can perform at all times such that the risks stay within the measures. So so let me show you how that works. So for that, let me give you a little bit of background on a theory that's called weakest precondition computation. Okay, and so this is a notation on the left. The syntax when we will say P, which is the precondition, S, where the S is the actual stage, what's happening at that stage, and Q, what is if the stage takes place, what's the result? What should be the conditions that should hold afterward? And the semantics for this is that if pre-state satisfies P, and then S terminates, S does the right thing, terminates, then the post-state will satisfy Q. Okay, that's the. Now the converse of that problem is called the weakest precondition computation. So here we are flipping this around. So WP flips this around. It says, what should be the weakest P that will allow the stage to satisfy Q? Okay. So remember that in the previous example, we had what should hold at the end. So we had what should be the conditions that should hold at the end. So we're going to start from the end and say at the end we kind of know this measure. We have to satisfy this measure. So what should be true for the stage before? Okay. So let's look at this example here. So this is the last stage. This is an FCN classifier. And again, let's not go into the details too much, but I think it suffices to say that the FCN classifier implements this operation here. Okay, it implements this operation, and given an input, it produces this output. Right. So the outputs will be the variables on which you would enforce the log loss, the uncertainty measures, right? So the question here is, given a post condition Q on the data outputs here, what is the weakest precondition of the stage? Right. And so I said, as I mentioned before, for this particular system, systems are ranked using log loss performance measures. So suppose that Q was that log loss is less than some epsilon. And so what that translates to then is that each of the probabilities P1 to P17 ought to be less than this epsilon 1 to epsilon n, which is essentially a constraint on the predicted probability of each body zone here. So given that, if you have P, post condition that is given like this, you can compute expectations of Xi by solving these systems of equations. Okay. And so that's the mechanism by which one would go about analyzing the data science life cycle to determine if the risks are going to be within the tolerance level. So continuing on, once you have done this exercise for FCN, now you get the constraints that you get on the input of FCN classifier become a post condition for the dropout. And so you're going to repeat this exercise now for the dropout system. So for this, the post condition is expectations on yi. Then again, you're going to do the same exercise, try to compute the expectations for xi's. And similarly, when you have done this exercise for dropout, now you go back as step 4. You can you look at attention weight layer, and because each attention weight layer has a mathematical formulation, so you can go and take a look at and try to understand how that's going to go, how the weakest precondition for attention weight is going to work, and so on. I won't be spending too much more time on this. So let me get to this another risk, which is unfairness. So when is a system considered unfair? So a data science lifecycle is considered unfair when it discriminates between people based on protected attributes such as race, sex, age, belief, etc. The discrimination occurs when certain groups get systematic advantage. So one of my recent students, Suman Biswas, and his thesis and papers have really extensively focused on this risk. So he also looked at the neural network and does analysis of the neural network. So his work has led to this fairness verifier, which verifies the fairness property of the neural network. And so the idea here is that he's specifically focusing on this property called individual fairness, and it is defined like this. It says that the model is individually fair if there aren't a pair of data instances x and x prime such that if the model predicts differently for those. The idea is that if the data instance only differs in that protected attribute, the model should give the same result. So this work essentially provides a formal guarantee of fairness for the neural network. And if the guarantee is not provided, then essentially it provides a counterexample where the network is not going to be produce fair output. And the method that it uses also works very similarly. So again, if you will think of, if this is a neural network, you will think of individual fairness as the post condition. And from individual fairness, you will determine fairness for this node. And from here, you determine fairness for this node, these nodes, and that leads to, if you are able to come up with some constraints for input, that becomes a satisfy. That means that the network satisfies fairness property. And if you're not, then you get a counterexample which tells you what is the path in the network that, if followed, could lead to an unfair situation. And the reason why this becomes a little bit complicated is because of the complexity of the networks themselves. So for n neurons, this query kind of divides into 2 to the power n branches, which cannot be easily parallelized. And that makes it a hard problem to solve. So he has a range of optimization techniques that he has utilized, he has invented to make the problem more tractable. So essentially, a review of how the reasoning works. So you have, like I said, the post condition here is this, which essentially is individual fairness. And then the post condition essentially gets translated into the fairness verification query. So here is one example of how that query works. So if the last layer is a sigmoid, this post condition using weakest precondition computation would become this transferred precondition for the previous layer. And this is essentially very similar to the example for uncertainty that I was discussing earlier for TSA. So I will take a pause here and see if we have any questions.
So this is really inspiring, but I'm wondering, so this notion of fairness of a network has nothing to do with the usefulness of a network, or, you know, I'm thinking about this cross entropy loss at the output. You know?
Right. So the accuracy. So in practice, what happens is that you need to optimize both accuracy and fairness at the same time, because you can't lose accuracy to make the network more fair. The fairness has to do with prediction of the network for different instances that only differ with respect to the protected attribute. Does that make sense? Okay.
Yeah.
Okay.
Yeah.
Okay. Okay.
Lot of things to learn, but yes.
Again, we can talk in more detail afterward. But in summary, one has to investigate both accuracy and fairness at the same time, because losing so the loss that he talked about and looking at just the fairness or looking at just the accuracy has the potential to lead to systems that are not so optimal. Because a lot of times there is focus on making systems more accurate, which tends to lose fairness. And then if you try to optimize on fairness, then the accuracy, if there is a loss of accuracy, that's not acceptable either. So often one has to consider them together. Yeah.
So just one more quick question. So we know that software verification problem is unsolvable, basically, and this one to me looks in design somewhat similar to software verification problem, right?
If considered in full generality, yes, but the networks are not. Let me put it this way: the network's architecture and the functions that are used, and the way the network is constructed, makes this problem tractable in most useful cases. In general, this is as I mentioned before. The problem is complex, as you have rightly noted. So the question is, can we solve it in most meaningful cases? And turns out that we can. Yeah. Doug, yes. I think he needs a microphone here.
So I'm just curious about how you would explain the example of Amazon that you gave, where fairness was an issue. Yep. Right.
So there the protected attribute will be gender.
Yes.
And their system would be, if we remove gender, their system should, if every other attribute is the same, their systems should either select both instances or reject both instances.
So my question there is, you could sort of think of failure of the system to be fair as being benign, or the failure is really a result of the biases of the people who, it's not clear to me that the people who designed that particular process what was it about them that somebody else had to discover that this was an issue?
So yeah, that's a very, very good point. I think, so if I understand you correctly, Doug, what you're saying is that, was there an intentional practice that led to this? And my understanding is that most times it's not. Most times it is not. There's no intentional harm that is intended. It's not considering. It's forgetting to think about it, so to speak. And again, in the observations that we have so far is that usually the protected attribute is actually not considered in decisions. It's usually the other attributes that are dependent upon protected attribute. That even if the designer of the algorithms are not considering protected attribute, they may consider these other attributes, which then depend on the protected attributes. That's kind of so. Again, to answer your question, is somebody out to do harm? No. But do we need to think about it? Do we need to verify the system so that no harm is done? Yes. Go ahead.
Professor Rajan, I have a quick question.
Sure.
So I saw that we use the sigmoid function there, right? But I learned that most of the neural network, we use the 10H function. So how do we select the function?
Well, this work would not be selecting functions. It will depend on the designer to select function. This work will look into given the function selected by the machine learning or designer, how would post-condition translate into precondition? So, because designers will often look at accuracy as a factor in selecting functions, so to speak. So we wouldn't be at a stage where we are recommending that you select this particular function. We are at a stage at the moment where we are saying, okay, if you have selected this function, what is its impact on the risk that you're trying to minimize? Yep, thank you.
So I have a very simple question.
Go.
So what do you do if your fairness constraints are not met? Like
what do you do if your fairness? Yeah, so that's an interesting topic, and actually it's an ongoing work that one of my students has, is that you try to repair the system. And there are various different kinds of repair strategies that, so think of it, if you're familiar with search problems, think of it as a search problem where mutation of the part of the network are a search operator. And you search the space of possible mutations of the network and evaluate each part of that space using both accuracy and fairness as a constraint. So I won't get into the details today, but I'm happy to talk to you about this. So you do have to do something about it, so to speak. It's so there's the work on mutation. Yeah, go ahead.
And so, have you thought about some differentiable versions of fairness so that you can? try to optimize
we
both
haven't.
these together?
We don't consider ourselves experts in defining fairness. We are looking at it. This is how the literature defines fairness. Can we validate it? So we haven't looked at that.
We have 2 online questions.
Sure, let's go ahead and take them, and then I will wrap it so that I don't take too much time from our next speaker.
Our first one is, you were discussing about log loss in terms of measuring fairness. Will this loss used for updating the weights of the NN similar to learning for accuracy or other performance metrics?
So I was discussing log loss for the uncertainty case. Log loss was a risk, was a measure for the uncertainty risk for the TSA example. And so what was the second part of the question? Can you read that again?
Will this loss used for updating the weights of the NN similar to learning for accuracy or other performance metrics?
That's an interesting observation. Could that be incorporated? Could that domain-specific notion of accuracy be incorporated into the backpropagation algorithm? Probably. We haven't really thought about that, but that's a very interesting point. If you wouldn't mind getting back in touch with me, my email address is my first name at istate.edu, and describe more of your thought. Maybe we can talk a little bit more.
So your email address is
Yep.
Okay. The second online question is, I completely agree with Dr. Rajan's desire to make data-driven decisions more dependable. But I think the more serious question is that many data-driven decisions are already better than the humans they might replace, notwithstanding their own imperfections. Examples include judge decisions based on whether they are made before or after lunch, police behavior that depends on the first name of the potential violator, biased bank lending decisions or hiring decisions based on any number of factors not related to actual ability, and so on. Humans are so imperfect that many data-driven decisions are better despite their imperfections. What does Dr. Rajan think about data-driven decision systems that fit such circumstances?
Again, we are not pitting humans against the machines or machines against the humans. What we should be interested in is understanding the limits of these data-driven decision systems. And this is a philosophical question that I would love to have over dinner if there's another one organized. If society is to make use of these systems on an extensive basis, we have to have some notions of some proof, some evidence that we can depend on these systems, and to what extent. And that's really what we are after. That we are after creating evidence. We are after creating thresholds under which these systems could be trusted. Yes. There is another question that Doug has.
So I guess, I sort of feel like there is an undertone of ethics involved in what you're talking about, right? Yeah, right. So, sure, these systems may be making better decisions than humans are making, but shouldn't it be a priority to sort of be sure that however decisions are made, that they are as ethical as possible?
Right.
So that
there is an at least we have an understanding of where these things are, and I agree with you completely. Thank you. Very good. So if there are no more questions, I would like to proceed and wrap up the remainder of my talk. So far I've talked about risks. So far I've talked about measures. Let me give you some insights into mechanisms that we are also working on. So again, mechanisms are additive to stages that ensure risks are within tolerance level. So we are focusing on these three kinds of mechanisms, more modular approaches to building life cycles. Here our focus is on black box neural nets, better quantifying what should be the contrast between different stages, and then localizing how to identify faults, how to identify problems, and location of problems. I won't get into the details of each of these. They're just, these are 1 hour talks by themselves, but I'll give you a little bit of flavor on what happens. So one of my students, he's soon graduating, Murangit Pan, he is looking into decomposing models to mitigate risk. So he gives this example where the image processing algorithm assigns labels to folks. And this is a very well-known example. I won't go into too much into the details of that, but essentially what happens is that black people are essentially labeled as gorillas by this app. And so the provider used the following mitigation mechanisms. So what they did was they had a faulty model, right? They had the faulty model that, and what they did was they suppressed that label. They said, oh, any time the model is going to produce gorilla as a label, we are just gonna not give that label at all. Okay, so this doesn't really solve the problem. The model still has problem. So what we would like to do, and my apologies for the slightly misformatted image here. So what we would like to do, and what he has shown that if we have a faulty model, if we have a working model, can we decompose that faulty model into a module, one for each of these labels, so to speak, and then make it possible to take good pieces from this faulty model and the good pieces from the working model to create an eventual model that works better. So he has shown that, in fact, this is possible. It's possible to really, and again, I would love to have a more detailed discussion with you about this. But the key idea here is really to understand and trace what are the parts of these black box models that are responsible for producing a certain output, and cut out those parts to make these modules. This has there is another way to do that. Which is that you can have a newly trained model, and you can decompose both, and you can take working pieces from both and put them together. Finally, you can also just take out that module instead of taking out this system. So again, I won't go into the details. You can see the details. There is in this paper we have which talks about decomposing deep neural network into modules. Another example is for localization. This is in this mitigation mechanism. What we are looking into is if you find a fault, what part of the network is responsible for that fault? And so this collection of work that is done by my PhD student, Mohammad Wardat, essentially identifies these mechanisms and shows to developers which part of the model has problems so that they can go fix. So with that, I will summarize my talk. Today I discussed with you the importance of ensuring the dependability of data-driven decisions because they are being utilized in safety-critical systems. We talked about some impacts of unreliable decisions. We talked about our work on D4 framework, and we showed some examples of risks where it can be applied. This work is far from done, so I would love to have collaborations from colleagues sitting here, colleagues who are watching online on this work, because there is a lot of work still to be done. Thank you very much for your time and for this opportunity. Okay.
Thank you, Ridesh. This was a very interesting talk. You covered an enormous amount of material. I wish we had more time for it. So our next speaker is Dr. Zheng Wei Hu. He is a data scientist at John Deere. He has a PhD in mechanical engineering, but he does machine learning work. His work all involves data mining, data labeling, visualizations, pattern recognition, developing machine learning, and deep learning solutions. So his talk will give you some idea of the extent to which machine learning is being used at John Deere here in Cedar Falls, Waterloo. Zheng Wei, would you please come? Yeah.
All right. So, good morning, good afternoon, good evening, everyone. So, thank you for joining this machine learning symposium. And also thank you, Doug and Said, for organizing this symposium. So, my name is Zheng Wei Hu. I'm currently a data scientist in John Deere. So, my talk today is about the application of machine learning to smart industry. Okay, a brief introduction of myself. So I'm currently working in John Deere System Health Analytics Group as a data scientist. So my daily work covers leading the innovation efforts in developing new machine learning methods and also to enable structured data to drive machine learning or to drive machine insights and to identify opportunities, define and implement new concepts for value creation. So prior to John Deere, I also have two experience either as a mechanical engineer and product lead in two industrial companies in China. I got my PhD degree in mechanical engineering in Missouri University of Science and Technology. My research focused on reliability analysis, optimization, machine learning, and statistics. So before that, I also hold my bachelor and master degree in mechatronics in China, and my research during that period was focusing on robotics, mechanical design, and control system design. So today I will cover 3 sections. So the first one is introduction to machine learning. The second one is reliability analysis based on machine learning. In this topic, I will cover the support vector machine algorithm. So the third section is the John Deere machine learning applications. So I will cover 3 subtopics here. So the first one is pattern recognition. I will introduce a binary classification practice in my products. And the second one is a multi-class classification problem. We'll see how we use the multi-class classification method for failure types identification. The third subtopic is failure detection and remaining usage life calculation. Okay, now let's see a brief introduction to machine learning. So before we dive into machine learning, I want to share a little bit about the history of industrial revolution. So as you may know, in the first industrial revolution, the steam power mechanized the production. And in the second one, we have the electrical power, which enables mass production. And in the third one, we have electrical power, which make it possible to automate production. And now we are in the era of the fourth industrial revolution. So the fourth industrial revolution is actually a fusion of multiple crucial technologies. For example, the Internet of Things, robotics, 3D printing, and big data analysis. So there's something in common for all those technologies. That is the smart devices, smart sensors. So we use all those sensors to collect informative data. But how can we get insights from the raw sensor data? That is exactly how machine learning plays its role. But what is machine learning? I think most people already have some idea about machine learning. So it's actually a subfield of AI. So AI is artificial intelligence. But it's not like AI. AI is trying to mimic human abilities, while machine learning is trying to train a machine or train the computer to learn how to model, how to predict things. So machine learning models actually look for data patterns to draw conclusions or insights like human does. So based on the different types of data, the machine learning can also be divided into supervised learning and unsupervised learning. So supervised learning is to develop predictive model based on both input and output data. So the output data has some different types. It may be some classes like the true or false or the RGB colors. And for other output data may be continuous data, a real number, like the stock, in the stock market, the price of stock, or the temperature, or the engine speed. So in that case, it will be a regression problem. So for unsupervised learning, is to develop an internal representation from input data only. The main algorithm is clustering. So in unsupervised learning, there's no output. So the machine has to find the natural groups and patterns from the input data only. For example, in the plot here, it shows the relationship between the engine speed and the vehicle speed. So there's no output. We only know this speed here. But using a clustering method, it can identify the different groups. So different colors means different types of vehicles. So that is unsupervised learning. But today we will focus on the supervised learning algorithms. Next, I will introduce some application of how we use machine learning in John Deere. So the first application is the See and Spray Select Ultimate System for sprayers. So as you can see in the photo here, there's a sprayer working in the field. And we saw that there are a lot of cameras. Actually, there are 36 cameras mounted on a 120-foot boom, which can scan more than 2,100 square feet at once. So this practice can greatly lower the herbicide costs, and which can cover more fields per day, and this can greatly reduce the non-residual herbicide cost by more than 2/3. So the technique here is a combination of computer vision and machine learning, which is to detect only the width from the crop plants, but ignore all the other ground without width. So that's why we call it see and spray. So the second one I want to introduce is the application. We use signals from the machine to classify what state of the machine is in. So this is actually a multi-class classification problem. So the input is the signals such as engine load, the vehicle speed, or the boom position, as the curves here, right? And the status is output. We want to predict what status the machine is working right now, right? It may be a loaded transport, it may be a dump, or it may be unloaded reverse. So this practice or this model can help the customers to identify what kind of status the machine is in. For example, it's working in a normal state or in an abnormal state to avoid potential failure or risk. Yeah, so the third product is what I'm working on. So it's about the connected product support. So we want, in my group, we are trying hard to eliminate or reduce the unscheduled downtime. So to do this, we first need to know what kind of data we can use. In this project, we are using the telematics data or the sensor data. So that is why we call it connected machines. So the connected machines is actually the machines equipped with a lot of sensors, and we have all the sensor data in our database. But to identify what kind of machine or the machine status, we want to identify if the machine is field or non-field. So for the field machine, in the model, if the machine is already predicted as field, we'll tell the customer, hey, the machine will be field or it's already field. You need to check it and see do you need to replace some components or parts. If the machine is labeled non-field by the model, we also tell the customer, hey, the component's still working, but we also calculate another parameter for the customers, which is called the remaining usage life. We let the customers know, oh, okay, this component may be filled in next 3 months or in next 1 year, so you need to prepare for replacement to avoid unscheduled downtime. So this is a goal for this product. Okay, so next section, I would talk about how we use machine learning algorithm for reliability analysis. So before that, I first want to introduce some important concepts in reliability area. Reliability is actually the probability that an item can function as desired during a designated time period without failure. So as you can see, we have a beam here, right? So the beam is subjected to 2 loads L, so on both ends. And we have a cross-section of the beam as the height H0 and the width B0. So in reliability area, we have a concept which is called the design margin, or the performance function, which is denoted as y equals to gx. So g is the performance function, which has a variable x. So x is actually the vector of the random inputs. So in this beam case, the random inputs is the load L and the dimensions H0 and B0. And y is the state variable. So why we call it a state, which means when y is bigger than 0, we'll call it means a safe status. If
smaller than 0 is a field status. So in this case, the performance function can be calculated by the strength minus by the stress. So it shows like this. So the probability of the reliability here is actually the probability of y bigger than 0, right? If y bigger than 0, the strength bigger than the stress, it will be safe. And we know the reliability, and the probability of failure will be 1 minus reliability. So this can also be visualized as the plot here. This is a stress-strength interference model. The failure region is actually the shaded area. What we want to do, or the reliability calculation, is actually to find the area of the failure region. Yeah, so the beam case is actually a component reliability analysis case. But generally, in industrial application, we want to, most often, we want to calculate the system reliability. So to do so, I will introduce a very simple system here. This is a serial system. So serial system means if there's any component in the system fails, the entire system will fail. Like we have, for example, here we have n components which is connected in serial, and in this serial system, to calculate the reliability, we have two common methods. The first one is use the reliability definition. We only need to calculate this integral here. The other way, in industrial application, we use another assumption, which assumes that all the components are independent. So in that case, the reliability can be easily calculated by R1 times R2 times R3 to Rn, right? So just do the multiplication for all the component reliability. I will talk more about this later. Now let's move on to next slide. So why we want to use machine learning to do the reliability analysis? So this is caused by the two challenges emerged recently. The first reason is nowadays more and more systems has multiple dependent failure types. So in this case, we cannot use the independent assumption, right? So because if we consider the dependence, the different components in the system rely on each other, or one failure of a component may affect the reliability of the other component. So that is complicated. We cannot directly use the independent assumption to calculate the system reliability. So the other challenge is that nowadays the industrial company functions more like an assembler. They may have their own in-house components, but they also outsource a lot of components from the suppliers. So that has another issue. For the in-house components, we know exactly everything. We know how to calculate the reliability using physics. But for the outsourced components, we don't know. We may know some information, but we don't know all of them. We cannot use the physics-based method to calculate the reliability. So that's why we need to using some machine learning algorithm to fit a model for the outsourced components using the testing data or the data provided from the suppliers. So in this research, our scope is we assume the failures are caused by excessive loads, and we have multiple failure types. So we will focus on only the first case here. We assume the system has multiple dependent failure types. So for the first failure type, we assume all the design information is known, like the design materials and the performance functions. And for the type 2 failure, we assume that we don't know the design details. We don't know performance functions, but we do have some data set or from the lab testing. So in that case, we can use the machine learning algorithm to predict to build the performance function. So that is the logic for this background. Okay. All right. Sorry. Okay. So as I mentioned here, for the failure type, we know all the information. We know the failure mechanism. We can use we can create a performance function and do the reliability analysis directly, right? So in that, for the first failure type, actually we can use the first order reliability method, which is a physics-based reliability method. We can just build a linear function using all the known information. So in this linear function, we have two parameters. The first one is lambda, which is the reliability index. Use the lambda, we can calculate the reliability of failure for this failure type. Another parameter is a unit vector alpha. So alpha is actually it's a unit vector related to the performance function in the standard normal space. So so for the machine learning algorithm I used for this research is the support vector machine. So so support vector machine is to find separating hyperplane to divide the different groups. In our case, we only want to divide the failure data and the safety data. So the algorithm is something like this, but we don't need, no worries if you are not familiar with these functions here. So what we want to do using the support vector machine is to get alpha vector, the unit vector. If we know the unit vector alpha, we know the hyperplane, and then we can build a similar function as the first failure type. Then we can combine them together for the final system reliability analysis. So so let's see. So let's see how we do this step by step. So for the first step, we can build a linear approximation function as a performance function. As I just mentioned, we only need to find the beta and alpha. Because we know everything for the type 1 failure, we can easily find the alpha and beta here. For type 2 failures, we know we don't know the performance function, but we assume that we know the reliability. We know the probability of failure, and then we can use this method to get the parameter beta. And then we use the support vector machine to fit a hyperplane and get a unit vector alpha. So see, now we have beta, we have alpha, right? So for type 2 failure type, we can also approximate a linear function like this. After we compare these linear functions, we see that, oh, they are very similar, right? So this is how we can use those linear functions to do the system reliability prediction. So the system reliability prediction, as I mentioned, we can use this integral to accurately calculate the reliability. So to calculate this integral, the only thing we need is the mu and sigma. So mu is just a vector of all the betas here. So and sigma is the covariance matrix, which is calculated by the alphas from either type 1 and type 2. Because we already know beta and alpha, mu and sigma is already available. And then we can easily, using a function, to calculate the reliability, thereby the probability of failure of the system. So that's the logic of this method. And now let's see a case to understand this better. So we have a cantilever beam here. So the beam suffers some forces, some distributed load, and some torques. Those two tables are showing the deterministic parameters, which are constant, and some random variables, which follows different distributions. This is how the uncertainty comes from. So this beam has 3 different failure types. The first failure type is a type. This beam has 3 different failures, and the first failure is a failure is a type 1 failure, and the second one is also a type 1 failure, which means we know everything for these 2 failures. We know the performance function, and then we can use the form or the first order reliability method to get a linear function for each of those failures, right? So, for example, for the first failure type, we have a function g1 with the parameters beta 1 and alpha 1 known, and for failure type 2. We have a similar linear function, and we know the beta 2 and alpha 2. And for the third failure, which is the type 2 failure, we don't know too much information, but we have the testing data. We can use the support vector machine to get the alpha, right? So beta 3 is already known because we know the reliability for the failure type for this failure type 2. So, yeah. So this is how we get using the support vector machine to get alpha 3. So we have the label data either safe or failed for this failure type 3, and then we just feed it into the support vector machine and get a hyperplane. It will automatically get the linear function with the unit factor alpha, and now we have the linear function for the third failure with the failure type 2. So this function looks like this, and use the system reliability function. As we know here, we only need the mu and sigma. So mu is actually beta 1, beta 2, and beta 3. We already know all of them. And sigma, so sigma is a covariance matrix. We can calculate all the atoms based on the alphas, right? So we already know alpha 1, 2, 3. We can also get everything in this matrix. So now we have all the parameters we need to do this calculation. So the final results will be something like this. And now I want to do a very simple comparison for the results. So in our proposed method, I mean the machine learning algorithm integrated with the physics-based reliability method gave these results. So it has the error 0.13%, and the true value here is calculated using the simulation, Monte Carlo simulation, which is a very common method in statistics to get a true value, because we assume everything is known. And this is the method I mentioned in the industrial application. So generally, we are using independence assumption to assume everything is all the component is independent, but we have a prediction error like 26%. So that's why we want to consider the dependence and use a machine learning-based algorithm combined with the physics-based algorithm to do the system reliability analysis. So so this research has been published in the Journal of ASME Mechanical Design, and the extension of this research is a one-class support vector machine. It's also published in another AI journal. So if you are interested in any of this research, you are very welcome to visit these two links here to check some more details. So I will take a 1 minute pause for questions. Yes.
So for cantilever, you show two types of, so type 1 and type 2, right?
Oh,
so,
right. Yeah.
I was under impression that basically type 1 and type 2 is for different systems, but here you have basically one system and two types. So what actually makes one type 1 and the other type 2 for the same system?
Oh, right. So, so the difference between type 1 and type 2 is for type 1 failures, we know a lot of information, like the design, the dimensions, like the material features, and also the performance function. We know how it feels, so we can build a physics-based model to do the reliability analysis. So in that case, for example, this beam, we know everything, and we can just calculate the reliability using the mechanism like this. But for the type 2 failure, we don't know the performance function, so we don't know why here. We need to figure out, or we need to approximate a linear function, y. And then after we get the linear function, we have the linear function with the same format as it from the type 1 failure. And then, like I showed here, we only need the alpha and betas to calculate the system reliability if we know both linear functions from type 1 failure and type 2 failure. So we know so type 1 failure is the performance function. The linear performance function is calculated by all the known information. The second type, the type 2 failure, the linear function is from the machine learning algorithm. And after we know everything of the linear function, we can get the beta and alpha, and only feed beta and alpha to the system reliability calculation function. We can get the final results. Yeah. Okay, so if there's, oh, sure. Okay, if there's no more question, I will move forward to the machine learning practice in John Deere system, system health analysis. So I will cover 3 different subtopics here. It's actually 3 projects I'm working on and I have worked on. So the first one is the pattern recognition. The second one is the multi-class classification. The third one is the failure detection and remaining usage life estimation. Okay, so let's see the pattern recognition. So this project, the motivation is every week we have a bunch of new claims, but those claims are either vehicle claims or engine claims. So in our team, we only focus on the engine claims. So we want to build a machine learning model to help us select only the engine claims through from all those new claims. So when I say engine claim, it means any claim related to engine failures. So the vehicle claim is all the other component failures with not related to engine. So yeah, so this is the original data. So it's a text format data from the warranty database. It includes the complaint text from our customer and the correction and cause text from our technicians. So this kind of data cannot be used directly for the computer program, right? So we need to do the data cleaning and also get the labeling. So the labeling here is actually the either engine claim or vehicle claim. So it's a binary classification. So, but yeah, again, we can't use the engine and vehicle directly. We need to label them to 0 and 1. So the labeling effort was done by our engineers manually before. So we have this training data. And then we need to convert them into something that the computer can recognize. We use the natural language processing techniques to convert the original data into a processed data. So we were doing the text cleaning and then create a corpus for the model. So the text cleaning is actually what we were doing is to remove the stop words, which make no sense to the analysis, and then we will remove the punctuations. We will also find the stems or lamb of the words, and then after this is done, we'll use the feature engineering to select the most important features and then put them in a vector as the input of the machine learning model. So the third step is to build the machine learning model. So here I use the deep neural network. Specifically, it's a long short-term memory. I think Dr. Rajan also used the same method, LSTM. So the LSTM is not like the general neural network. It has a backward feeding mechanism which could grasp the relationship between the words correctly and more efficiently. So the prediction accuracy is around 92%. So this model is already used in production for a while. And then, yeah, we can see the numbers here. So before we use this model, we need to spend around 400 hours per year to select the engine claims for our group. And now the automated algorithm we only need to spend 25 hours per year for the final check. So the efficiency has improved around 94%, right? So yeah, it makes a lot of sense. Okay, next I want to explain another product, which is a multi-class classification algorithm. So the objective of this function of this product is in our warranty database, we noted that for each claim we have a specific failure type, but we have a lot of claims. We want to automatically identify what kind of failure types belongs to this claim. So the data we are using here is also from the warranty data. We have the part number and also the warranty text. So this text is the same as the vehicle engine identification product. So we have these two features. And also, we know the label for each claim here. So the label is actually the failure types and also the target we want to predict. So yeah, so the data processing process is pretty the same as the previous product. We do the data cleaning, so remove the missing values, remove the duplicates, and in the data processing process, yeah, it's also very similar. We use the natural language processing techniques to remove a lot of useless words and convert everything into a vector. So yeah, let's see a example here. For example, we have this sample. We have this claim. The part number is something like this, and the warranty text something like this. what we did is remove the stop words, which make no sense to the claim, right? Like the Z, is, and up. So we just remove these words and convert them into the lamb or stem of the words, and combine them into a vector. So the vector here shows, actually the values here means how many features we have in total, and how many labels we have in total, something like this. So after we combine all of them into a final vector, we can put them into the model. We can feed them into the model to train the model and use the model for prediction. So for this specific case, it's an actuator problem from the turbocharger. So we have the ID 64, and then we go back to the labels for the failure types. We can convert it back to the text format of the failure type. So the model I used for this product is the extreme gradient boosting, or XG boosting. So this is an example model which has a very fast. It's very faster than the other algorithms. So the accuracy is around 85%. It's also, it's okay to use in production, and we are still working on this to improve them to improve the model performance in the future. Okay, so the multi-class classification model was used in the last product. We are using them in warranty text, in the warranty claim prediction. But actually, not all the text are clean as warranty data. For example, some of our new claims may only have the text. There's no part number in the features. Then how can we do the prediction? How to predict the failure types on these claims? We need to collect the part number from the text, and then make them have the same format as the previous trained model. So this is another technique in natural language processing. It's a regular expression. So using regular expression, we can extract the part number from the new text, and then the previous model can be used directly for the failure type prediction. So let's see another case here. The claim 6, we have the original text like this. And when we extract the part number from the text and convert it into a vector, and then apply the previous trained machine learning model to this vector, and we will have the prediction of the failure type. So the number is 69. So why we put 69 here? So it's actually a voting system. It will select the prediction with the highest probability. So the one with the highest probability means, okay, this prediction is most probable, the correct failure type. And then after we have this number, we'll go back to the label, which already converted, the failure types already converted into some numbers, right? So the 69, we find 69 here is actually an ECU failure type. The ECU is something, it looks like this. So this means for this specific claim, it's an ECU claim. There's some failures in ECU. So the accuracy for this application is around 75%. So it's not as high as desired, but we are still working on this to get more data, to clean to further clean the data. Or maybe we'll combine some other algorithms with the XG boosting to improve the model performance in the future. Yeah. Yes, sir.
So we have three remote questions.
Yep.
The first one is, even though the accuracy is greater than 92%, are sensitivity and specificity considered in the binary model?
Oh, sorry. Can you repeat that?
Okay.
2%. You mean the reliability here, or?
It says, even though accuracy is greater than 92%, are sensitivity and specificity considered in the binary model?
Oh, in the binary model. Okay. Oh, right. So could you repeat the second half for the question?
Okay. And then Scott, feel free to enter any clarification you want.
Yeah.
Even though accuracy is greater than 92%, are sensitivity and specificity considered in the binary model?
Oh, yeah. So yeah, that's really a good question. I think we use the confusion matrix, and yeah, definitely the accuracy here is the average accuracy. So the recall and precision is as good as this, because our data is not highly balanced. It's not highly imbalanced. We have in the training data set, we have almost the same vehicle claims and engine claims. So yeah, so the we already consider all the metrics. So this this average accuracy, I think is good. Is as good as the recall and precision.
Thank you. Next question. How are you handling domain-specific technical vocabulary? Any specific embedding help in your case?
Oh, yeah. So, yeah, in the vector here, we do use the domain knowledge. Is actually we get it from the engineering side to make sure what kind of failure types or what kind of keywords we need for training this model, and this will be this also help us in put some more words which have a lot of impacts or which make no sense. We'll just put them. We'll just put the useless words into the stop words to remove to further clean the data. And yeah, we do already consider the domain knowledge in the analysis. Yeah.
And then the third question: how about transformer models for the warranty claim? How are performance improvements compared to the LSTM models?
Oh, okay. So yeah, I think here, right? Yeah. So before I use the LSTM model, I do tried a little. I do tried some other algorithms like the logistic regression or the normal deep neural network. But after I compare the performance, the LSTM, especially the bidirectional LSTM, has the best performance. I think it's like 10% more accurate than the other algorithm, than the normal neural network.
Thank you. Oh, we have another question.
Oh, sure, please.
So I was wondering if these prediction accuracies that you're showing, are they in the test set, or are they after being deployed?
Sorry.
So basically, I was just wondering if these results, right, that you have shown throughout your slides, are they like the results that you're getting from your test set, right? Just the test set, or have you actually deployed these models, and do you really use them in your day-to-day operations, and are these results from like in that setting?
Actually, yeah. So this the vehicle engine identification and the multi-class failure type prediction are already used in production.
Okay. And so do they get about 85% accuracy in production?
Yeah. So yeah, well, that's really a good question. It also depends on the new claims, the new data. If the new claims the text is clean, then the prediction is higher. Okay, that's why I put bigger than 92%.
Okay.
So generally, for the bad claims, with bad text, we have 92%. But for some claims which has a lot of technical words, there the prediction is as high as 95 or 96%.
Okay. Wow.
Yeah.
That's
So-
amazing. Thanks.
Right. Yeah. Thank you. All right. So okay. Thank you, sir. Then I will move on to the next one. Okay. So this is the project I'm currently working on. It's failure detection and remaining usage life calculation. So the background of this project is nowadays, because we are already in the era of the smart industrial, right? So we do have a lot of data from sensors, from the telematics data. So we want to use the telematics data to get more insights, like to predict the potential failure in real time. So this is what we want to do here. We collect the telematics data first. So the data include the diagnostic codes, include the engine speed at loads, or temperature, or pressure, or whatever from the sensors. And now we want to know, can we get a prediction for failures, or for the working status using this kind of data? And the answer is yes. So we collect this data and do the data cleaning and the data processing, and then we feed them into a binary classification model, because we want to know if it's a failure status or normal status or safe status, right? So it's a binary classification. And so the output of the model is either 1 or 0. If it's 1, it means failed. We need to tell the customer, hey, it's already filled, or it may be filled in the near future. We need to take care about that components. And if the prediction is non-filled, we'll put a 0 there. So the non-filled machines, it means the component is still working, but it will be probably filled in the future also, right? Then we'll calculate the remaining usage life for the non-filled components, and let customers know how long or how soon this component may be filled in the near future. So this is what we call the remaining usage life calculation here. It's actually combine the machine learning prediction with the reliability analysis. So the machine learning prediction will be the first step to identify if the machine will be filled or already filled. The reliability analysis will be the second step to let the customer know how long the machine or the components can still be in service as normal. So here we are focusing on the EGR cooler. So the EGR cooler, EGR is short for the exhaust gas recirculation. The EGR cooler is to reduce the temperature for the exhaust gas, and also to eliminate the harmful gas like the nitrogen oxide and the like. So I put 2 pictures and link here. If you are interested in the EGR cooler, just visit the link. Okay, so those are the features we collect with our engineers. So those are the most related features with the EGR cooler. And for example, some temperatures and some pressures, and also the engine speed at load. Those are the features closely related to EGR cooler performance. And also we noted that there are, for the engine speed values, they are split into, they are based on different load percent interval. If I use them separately, combined with the other features, I found that the model doesn't work very well. And then I talked with my coworkers and the other colleagues in my team, And we found that if we combine them together, actually it's not combined. We use a weighted sum model to convert a new feature like this, using all those ending speed at different load percent. And then we use this new feature with all the other features. The model performance improves a lot. So yeah, so I think that's how the feature engineering affects the model performance. And the result for the current analysis is around 94.5%. I mean the accuracy. And also we put a confusion matrix of all the metrics to compare the accuracy, either the recall or precision rate. So yeah, now we know how many machines may be filled, how many machines already filled, right? So as I mentioned, we want to calculate the remaining usage life for the customers using a reliability model. So how to build the reliability model? Here we are using the Webble++ software, and then by feed all the values of the different sensors here, we can get multiple different reliability models. And then we compare the models using the testing data and find the best one. So the best one here we are using is a log normal reliability model. I will show the results here. Yep. So we have two plots. Those are the output of the reliability model. So the one on the left shows the goodness of fit of the model. So the second one is exactly the unreliability versus time, or in other words, unreliability is actually the probability of failure, right? So it shows the probability of failure over time. The blue line here is exactly the reliability model. For example, if we let's see, we have a point here. So the point will tell us at a specific time point what the probability of failure of this machine will be. Or in other words, let's say if we select one point in the reliability model, we'll know if the machine has a 90% probability of failure, what's the time? What's exactly the time is on? So yeah, for example, we can tell the customer, hey, your machine will have a 99% probability of failure in the next 3 months, right? So before the end of the next 3 months, we can tell him to prepare for the replacement, right? To reduce the unexpected shutdown. So that's the goal of our product for this one. I'm still working on this product. I think in the future we will have more insights. Okay, so a brief sum up here. So we talk about the reliability model, which is combined with machine learning algorithm. And also we talk the binary classification for the vehicle engine classification. And also we talk about a multi-class classification for failure types prediction. And also we do the potential failure identification for a specific component like the EGR cooler here, right? And then in the end, we use the result from the machine learning algorithm to do the reliability prediction. Actually, it's the remaining usage life calculation for our customers to prepare for the planned component replacement. So in our future work, I'm going to spend some time on stream data analysis because we already have a lot of sensors equipped on our machines. We are able to do a lot more analysis using the connected support method. So the stream data can help us to do real-life machine monitoring and machine learning modeling to get some more real-time insights. So the second one is we are going to embed machine learning in the entire product development process. So currently in my group, we mainly focus on the quality and safety using machine learning algorithm. But actually, this can also help to improve our designs, our manufacturing, and also for our marketing, for our sales and service in the future. So yeah, finally, the goal of everything we are doing here is we want to improve the business strategy, right? And also to help our stakeholders to optimize their decision making. So yeah, I also put some links here for all the terms, for all the methodologies I talked about in this presentation. You are very welcome to visit any of the links if you are interested in. So yeah, I want to give my thanks to my managers, Anu and John, for their support for this machine learning symposium. And also I want to say thank you to Said and Doug for the organization. Thank you, everyone. That's my talk. Yeah, sure.
Thank you. So in the second part of your talk, you discussed a reliability analysis, and was that at a system level or was it at a component level?
Oh, so which system you mean?
Meaning that was it? Did you analyze the entire system, and would you analyze the entire system or just pieces of the system? That was the second part of your talk, last part of your talk.
Oh yeah, I think it's for the component level at this moment.
It's for component level.
But we can I mean include some more components or parts, and to make it work in the entire system.
Okay. And so what's your sense in? So there are probably theories for how to do that without using data. Right there. What's your sense of how this? How your data-driven approach, machine learning-based approach, compares to the physics-based approach of doing the same task? Do you feel that your machine learning approach is maybe more effective or less effective?
Oh, right. Yeah, that's really a great question. So even during my PhD study, we want to figure out can we use the machine learning algorithm to totally replace the physics-based reliability analysis, right? But the answer is, I think, to my experience, the machine learning algorithms still have some limits compared to the basic physics reliability method. Yeah, I think in the future in the near future we may still to combine them together. So
that's great. Thank you.
Yeah, thank you. All right, thank you, sir. Yeah.
Thank you, Zheng Wei, for a very nice talk. Very nice. You explained the things very well. And I'm not surprised that the John Deere stock price is going up and up because they're using machine learning so effectively. So our next speaker is Vijay Adhikari. Dr. Adhikari is at the Department of Computer Science at University of Iowa, and he builds new algorithms and deep learning architectures incorporating epidemiological domain knowledge to solve real challenging problems. And he has won wide recognition for his work. He has received several awards for that kind of work. And I will not take more time, ask Vijay to present his work. Thank you.
Thank you very much for the kind introduction, Dr. Silmani. First of all, I'm Bizay Adhikari. I'm an assistant professor in the Department of Computer Science at the University of Iowa. I would like to thank the organizers of the symposium for inviting me. I'm very excited to be here. And today I'm going to talk about forecasting epidemic outbreaks in real time. This is the brief outline of my talk. I'll start by motivating epidemic forecasting. Then I'll talk about the layout of the land before COVID-19 pandemic started, and at that time we were basically doing influenza surveillance and forecasting. Then I'll talk about two specific models for COVID-19 pandemic response that we developed. Right, first one is the model deals with forecasting influenza in presence of COVID-19. So because they have some symptomatic similarities, there were some challenges there. And then the next model basically deals with forecasting COVID-19 incidents and hospitalizations. Then I'll spend some time talking about some of the open problems in the area, and probably these problems will be solved in the next few years. So let's start by motivating these problems, right? First of all, as we all know now, epidemics are very costly. They have both the high economic and public health burden. So this is an example from 2018-19 regarding influenza in US. So there were more than 18,000 deaths and more than 289,000 confirmed hospitalizations only due to influenza in US. Right? And the cost of battling these cases is estimated to be more than $27 billion per annum. So these are very, very big numbers. And I'm not lying, because if you just search for these things online, there are many reputable sources which will agree with me. And so when the COVID-19 started, things just turned upside down, right? So this is a snapshot from Statista, and it basically shows that all these states in red were running out of ICU beds in December 2020, right? Even in the United States. You can just imagine what the situation was like in other places. And so the impact was not just limited to health, right? If we look at this plot, it basically shows unemployment claims that were filed. And so this curve here is on May 2. So this is amazing, that the pandemic really started hitting US in March 2020, right? And by May 2020, there were more than 33 million unemployment filed, right? So so the pandemics and even epidemics have the power of impacting our lives in many different and negative ways. So we understand that these are big problems, right? But why does forecasting help, right? Why does forecasting what's going to happen? Why does that help? So the first thing to note here is that an accurate outlook of what's going to happen in future, right? Basically, how many cases are there going to be and how many hospitalizations are there going to be? It helps public policy makers, right? Government officials, healthcare providers to allocate right resources at the right time to the right place, right? And as we saw earlier, there were more than 15 states which are running out of ICU beds. If we had known a priori that these states will basically have spikes of cases, we could have allocated critical resources like ventilators, ICU beds, even healthcare professionals to those regions, right? It would have been more smart response. Also helps inform public policy, right? So at times, government may have to impose some stringent policies such as shelter in place, mask mandates, and so on. And if we have this accurate outlook of the future, it basically helps public discourse, right? So it facilitates conversation and makes things easier. Also helps with preparedness, right? Not just at government and policy level, but also at individual level and familial level, right? You may want to, buy lots of things, right? So that you don't have to go out, and you and your family could be better prepared. So it has, a lot of applications, and accurate forecast can help our lives in case of epidemics and pandemics.
So now let's begin with basically looking at the layout of the land before COVID-19 began. At the time, and I will take influenza as an example here. It's by no means the only epidemic that was there before COVID-19, but we'll just look at it as an example. So FluSite is an annual influenza forecasting challenge that's hosted by CDC, right? And here we were asked to make forecasts based on the WILI values. So these weighted ILI values are basically, the weighted representations of number of fractions of outpatients who visit hospitals with influenza-like symptoms, right? So with no other known causes. And so this is what the snapshot of the old FluSite challenge website looked like, right? So these solid black line was basically the actual observed data, right? And so the forecasts were made at this time. So these remaining curves were not observed at the time, and these small snippets were the forecasts submitted by different research teams. One of the curve was our model. Now, because of COVID-19 and some symptomatic similarities, the CDC has shifted to hospitalization. So basically the problem now is to predict confirmed influenza-based hospitalizations, but the method that I'm going to talk about today in terms of WILI should still be applicable to this setting. So let's look at how these data are being generated, right? So and we'll take Illinois as an example. So basically, what CDC employs this network of healthcare providers who report the percentage of patients that they get who have influenza-like illnesses, right? So, and influenza-like illness is basically defined as a disease having symptoms like cough, and runny nose, and so on, without any other known causes. And so these numbers are then submitted to CDC. CDC then compiles them, aggregates them, and weights them by the state population. And and then they basically release a compiled time series data, right? And they release one data point each week for each geographical region, right? So over time, what we get is we get this time series data where you have time on the x-axis and you have some values on the y-axis, right? And you get a curve that looks like this. And this historical WILI data is publicly available, and so the first season that we have such data is from 1997, and anybody can download this from a CDC website. So based on this data, the CDC was asking us to basically solve some forecasting problem, right? So let's try to look at this problem formally. So in this problem, we are basically given the historical seasons. So whatever happened till last year is already observed, right? And for the current season, you have observed the data till last week, right? So that's basically what's happening every week. And so you have these two things. You have a set of historical fully observed seasons and a partially observed season till the current week for the current season. So basically it's the ongoing year. And now the goal is to basically predict few things. So the first prediction target was future incidence for the next 4 weeks. So what's going to happen, given the data that we have till the current week, what's going to happen in the next 4 weeks? The next problem was to predict the peak intensity. Basically, what is the maximum intensity of influenza cases that you're going to see over the entire period, right? Throughout this entire season, what's the maximum value that you're ever going to see? The next problem was to predict the peak time. When will this maximum value be observed, right? And that's an important problem because that's when the hospitals need to be most well prepared, right? That's when the demand hits you the hardest. And similarly, the last problem was to predict the onset, and it's basically a way of representing when the influenza season actually starts off, and it's basically defined as the first of 3 consecutive weeks when the WILI values are above a certain predefined threshold, right? So it's basically saying if the cases cross this level at some time, that time is when we start preparing things, right? So that's what this problem is trying to capture. And for machine learning folks, this is basically a time series forecasting problems, right? So you are given a bunch of time series, and you are given a query time series, and you want to predict some characteristics of the query time series. So there are some existing approaches even back then to solve similar problems. The first classes of problems are statistical approaches, where you just fit a predefined statistical model on the historical data, right? Some examples include regression, ARIMA, and so on. So a drawback here is that they are typically too simple, right? And the other thing is, they have nothing extracted from the domain, right? You are just, you have a backbone skeletal function, and you're just trying to feed that to your data. So, and at times they also lack interpretability, right? So you want to basically communicate with CDC saying that this is why I'm predicting a particular value, and these models lack that. On the other hand, there are these mechanistic models, right, which use disease models like SI model or SIR model, right? And then they basically, these are motivated by the domain and exactly the biology of the disease spread, right? The actual mechanistic process through which the disease spreads. And what you do is you basically calibrate your model. At times you can use various factors like mobility and weather, but not too many of such external factors could be included because it's very hard calibrating these things. And a drawback of these methods is that they require a lot of calibration, and at times they are too rigid to generalize well, right? So if you just use SIR, you are going to get a smooth curve, but there are these things like reporting patterns, right? Things go up and down, spikes we see in the COVID symptoms, COVID cases. Those things are very hard to be captured. So this motivates our approach, right? So now I'm going to show the overall overview of our approach. So what we first notice is that if you basically look at the past historical seasons, you see clusters of historical seasons, right? So here I have basically drawn 4 historical seasons, 2010, 12, 13, and 16 in different colors. So if we look at it, the green and the red curves look very similar to each other, and the black and the blue curve also look very similar, right? So now if you knew the fact that blue curve was going to be very similar to the black one a priori, like if some oracle tells you that, you are trying to predict the blue curve and blue and the black are going to be similar at the end. If somebody had told you, and you could, if somebody had told you that, you could basically say, okay, if that's the case, then I'm going to look at the trend at which the black curve is going, and I'm going to predict the blue is also going to go down, right? So that seems reasonable. So, that's why we try to use clustering for prediction, right? So you cluster the seasons together and then use the clustering to basically make forecasts. But something interesting happened, so we saw that, the similarities of the seasons, they could change over time. So this is a curve, so basically visualization of different seasons for HHS region 1 of the regions predefined by HHS. So the black curve here is the 2012-13 season, right? And what we saw was that in the beginning, right, when the season was starting, it was very similar to the 11-12 season here, right? In this red band. These two curves were the most similar one. But as that season progressed, these two started to diverge, right? It started flattening out, but it went up and down. At the same time, 2003-04 season was very similar to the 2012-13 season, right? And then again, towards the end, these two curves started diverging, but these two, started being similar, right? So the evolution, basically as the season progresses, the closest season that you have to the current season that you have, right, basically that you're trying to forecast for could change, right? So static clusterings are not enough, and you need to basically, update your clustering. And we also wanted to use, to basically do this, we had to use a deep learning architecture. So, our basically idea can be summarized as dynamic deep clustering for prediction. And, as we have in epidemiological domain, there is very limited data, right? So you had to be aware that, your problem has data sparsity and deal with that when designing deep architectures. So a brief summary of our method, right? It's an end-to-end architecture which automatically learns meaningful representations of historical incident curves at the time of prediction, right? So this is where this dynamic clustering component comes in, and it predicts various metrics of interest for partially observed seasons for the current influenza season, right? So it has to be basically, be able to solve all these 4 tasks that I highlighted earlier. And it was one of the first deep learning approach for influenza forecasting. So now let's look at each of these components of our method in more detail. Right? So the first component is the input encoder. So here you are basically, you take the snippets of the current season that you have observed till time t, and you want to learn its latent representation, right? So what we basically did was we are given this data. Basically, these are real numbers from starting at week 1 till week t, right? Week t is the current t. and you basically use some sliding windows to generate representations like this, and then we basically pass it into LSTMs. So turns out, just doing this is not enough, because CDC goes back and revises the data, right? So this week they may have said, last week's value was, like a 2.3, but next week they may say, you know what, we actually made a mistake with 2.3. It's not 2.3. Some of the hospitals gave us the data late. It's actually 2.7, right? So they may go back and change the data. So there is this, like inherent unreliability in the latest data, right? So the data that you saw recently, it has higher unreliability. And to basically address that, you want to assign different weights to the different part of the data. And like you can easily do that by using attention layer on top of the, like any sequential model that you have. So now the question is, can you just take that and then, solve your regression problems, right? Turns out not quite enough, because, it works well in training, doesn't generalize, right? And the issue here is that we have very, very limited data, right? And you are trying to learn this LSTM model with like a handful of time series. That's not going to work. Model easily overfits, does not generalize. So the question is, what do we do now, right? So basically, as we saw earlier, there are these informations in the clusters of seasons, right? So, and these are not being captured properly. So you need to extract those information in a bit more implicit way. So basically this takes to our idea to embed historical seasons, and we want to embed the historical seasons to capture the similarity with the current season, right? So now the issue is, your previous seasons, you have observed them for 52 weeks, right? You have observed everything, but the current season you have only observed till week T, the current week, right? That could be 10, 20, wherever you are at. So the first thing that you can do is basically, cut all the seasons till week T, right? So you have these small snippets of all the previous seasons. Now they are of equal length, right? And you can do whatever you want with them. So we basically use these snippets of the historical seasons to learn embeddings, right? And the way we do that is, by using one of the deep embedding clustering, and it basically has an autoencoder architecture, right? So if autoencoders basically, if this is the input, it basically tries to reconstruct the input while mapping the input to a latent representation, right? So this is where the representations are. And in the representation space, you have some clustering loss defined. The clustering loss is basically a KL divergence between two distributions, P and Q. So Q here is basically a student's T distribution, and it's basically trying to measure the distances between, say, cluster centroids and each of the data points, right? So that's all this is doing. And P is a like a self-supervisory target distribution. And what it's basically doing is, it's like squaring the terms of the Qs. And what that does is it basically says, I want a bit more confident cluster assignments, right? You have to pick one of the clusters. You can't just be like, I belong 0.5 to one cluster, 0.5 to the another cluster. So it basically tries to avoid that kind of situation. And, this is like self-supervised approach. So once you have that, and you have, the clusterings defined in this latent space, right? So you basically have meaningful embeddings of your seasons where the clusterings is defined. So, but the problem here at this point is that, not all data is being utilized, right? And we have, like data limitations to begin with, right? So, and we don't really want to throw away the data that we have. So how do we basically, take the remaining of the data? So that was the question. And so our idea was to basically, do the same process and embed the full length historical seasons separately, right? Don't look at the current partial season. That's only observed till time T. Just look at the data that you have till last year and learn their representations separately, and then learn a mapper between these two embedding spaces. Because for all the historical seasons, you have both the embeddings for the snippets, right, and the full length historical seasons. So if you can learn a mapping between these two embedding spaces, for the current season, you can just apply the mapper, right? So that was the big idea. And so basically, we exactly did that, right? So first we learned the full length embeddings for each historical seasons by using the same idea as I just described earlier. And it results in the embeddings, full length embeddings for each of the historical season. And then we train an embedding mapper between these two spaces. And basically what is this trying to do is like minimize the difference between the full length embedding and the mapped version of the snippets embedding, right? And once you have trained this mapper, for the current season, you just pass it through the mapper, and then you get the embeddings for the current season in the space where everything is observed, right? And so once you have that, you just pass it into a decoder and solve your regression problems. So the task one was basically future incidence prediction, right? So given the current snippets, you wanted to predict the actual values of what is going to be observed in the next 4 weeks. And that can be modeled as a regression problem. So our decoder architecture just had a feed-forward neural network with L2 loss. Similarly, the next problem was peak intensity problem. What's the maximum value that you're going to observe anywhere during the season? That's also a regression problem. So we had a very similar architecture. The third task was peak time prediction. So now we model this as a classification problem because you have to basically predict the week when the maximum value is observed. So we basically modeled it as a multi-class classification problem with 52 possible weeks, right? You just had to predict which week. And so our decoder had a feed-forward network with softmax loss at the end, and softmax layer at the end, and we had a cross entropy loss. And the onset week was also a time prediction, so we use a very similar architecture. So now to train the entire model, right, we basically wanted to minimize the sum of all these losses that we had, the embedding losses, the mapping losses, the prediction losses, and so on. So this was a very complicated network, and so we had to employ a specific learning procedure where we pre-trained the clustering models first, and then trained the embedding mapper, and then retrained the entire model jointly. And to for each of the training process, we just use Adam optimizer. So now let's look at the experimental results, right? So the data set that we had here was the publicly available WILS surveillance data that was released by CDC. And these were our baselines. So EV was an empirical Bayesian approach, and it was, at the time, this method had won the flu-site challenge for 3 or 4 years consecutively. So it was one of the best method back then. ARIMA is, like a autoregressive method. HIST uses take historical average of all the seasons and use the average to make prediction. KNN, you select, the closest season to you, some K number of closest seasons to the current snippet, and then, take their average and make predictions. LSTM is, just an LSTM. So we wanted to ask some specific questions in our experiments, right? The first question was, how well does our method perform in different tasks at the national region, right? So there were 4 tasks. And basically, so I have plotted the curve performance for each of these tasks. So the first plot here is for future incidence. The second is for peak intensity, peak week, and onset. And on each plot, x-axis represents different seasons, and y-axis is RMSE, right? Our method is in red. So since this is RMSE, lower is better, right? So that's basically the takeaway. So as you can see, our method is, almost the best in most of the settings, and whenever it's not, right? So for example, here it's not as the second best, so it's still pretty competitive. So recall, this is real world forecasting problem, right? So, coming up with a method that beats all other methods in all the setting is very, very hard. That's what we have learned. So now the next question is, okay, in national region, if you look at US as a whole, it works pretty well, right? But if you look at, a finer spatial resolutions, does the method, still do good? So we repeated the same experiments, right, for different regions. And there are these 10 HHS regions, which are basically group of states in different regions. And we repeated the experiments for all the regions, and I'm just showing these for 3. Again, right, so these are for 4 different tasks that we're talking about. Our method is in red, and this is lower is better because we're measuring RMSE. And again, similar result, right? So in many of the cases, it's best, and whenever it's not, still second or third. So it's pretty competitive, even when it's not the best method. So, and once we had this method, right, we basically participated in the 2018-19 flu-site challenge with Epidemic. And so in our first year of participation, so it was the most accurate model in HHS regions 1. So for the northeastern region, and there were more than 40 teams participating at this challenge at the time, and so this was the best model back then. So we're all pretty happy, but then we started seeing these news, right? That saying that there is a mysterious virus making rounds in China. It's not really SARS. What it exactly is. And we started seeing, some weird patterns in influenza data, right? So usually in March, all historical seasons, the cases go down, right? Because the weather starts getting warmer, right? And flu activity tends to go down. But a weird thing started happening, right? So this is region 2, which includes the state of New York, and region 10, which includes the state of Washington. The cases started going up in March, right? So influenza, so basically, this is like so the data is trying to measure the influenza cases, right, in these regions, and this data started going up. So, it basically turns out that, so what was happening was, since COVID and influenza have symptomatic similarity, right? So this data captured by ILI-NET was, mistaking COVID cases to be, ILI-like influenza-like cases. And these ILI counts were being affected by two things, right? So first was this COVID contamination, right? So the COVID was being spread, undetected. And and if you remember, New York and Washington were the two states where, we saw first major outbreaks, right? And these were being captured by the influenza cases, right? And once, things started taking off, right? And people just, started shutting off everything. The healthcare seeking pattern changed drastically, right? People stopped visiting hospitals for anything less than emergency, right? So, the curves started falling off very quickly. And this scenario basically motivated new kind of forecasting problem, right? So it's like forecasting influenza in presence of COVID, right? When these two signals were being mixed. So this is a visualization of all previous seasons, right, in the background. And the 2019-20 season is in the bold here. And as you can see, none of the prior season had more than 2 peaks, right? But this one clearly has third peak here. It had to go down, but because COVID started around this point, the flu activity, basically these ILI counts started going up, and once lockdown started happening, it quickly fell off, right? So now the question is, how do you, forecast these kind of things, right? So this is not unique just to COVID and influenza, right? So we could have another outbreak in future, which could have, symptomatic similarity with some existing diseases, and these kind of patterns could emerge there as well. I think the power went off.
Just had a little power issue, and it'll just take us a minute to fix this.
Yep, sure. Yep.
Sorry, I might have missed it, but what are the features that you're using for your classification?
So, in the influenza forecasting problem, right, input is just the time series.
Okay.
So we do not have any other information at the time.
What is the time series?
The time series is essentially, the WILI values, right? So these are basically these numbers represent the fraction of patients who visit hospitals with influenza-like illness symptoms.
And then you had 6 methods that you are comparing. You're using the same inputs for all of them?
Yes.
Okay, thank you.
So because you mentioned the mechanistic methods, so in your method, it does not consider any type of infectious mechanisms or any kind of genetic data or immunology data, and doesn't consider any of those, right?
Yes, so the influenza forecasting method is purely data-driven, right? Mm-hmm. And so, we'll get to, COVID ILI and COVID infection forecasting. There, we use, some mechanistic features, not the mechanistic process itself, right? We don't model how the disease spreads. That's one of the open questions, right? And problem that we're currently working on, how to, get a model that does both, right? Ingests data right, that you have observed in past, and also take, the mechanism of how exactly the disease spreads, right? So how do you get a mixture of data-driven model, which also, mimics the SIR process. So that's one of the, open problems and something that we are working on currently.
Okay, because when you made your comparison with other models, none of those were mechanistic models.
No, the empirical base is, it's somewhat mechanistic because, it has skeleton of the curve, and, that's basically motivated by the domain.
Yes, I'm just curious that how does your model compare in terms of accuracy or efficiency with the mechanistic
Okay,
model?
yeah. So that's a fair question, right? So these methods that were participating in the CDC flu site challenge, there were many mechanistic processes. Mm-hmm. Some of the teams were just doing SIR and, predicting the influenza based on that. But, for predicting WILI counts, there are some drawback of using mechanistic processes because, look, the data is not asking you to predict the number of flu cases, right? It's asking you to predict WILI values. So there is a mismatch between the data and the mechanistic process itself. Okay. So for COVID hospitalizations, again, the same, right? Mm-hmm. So your model will give you, the number of cases, right? Or if you model it correctly, even the deaths. But the problem that you have been asked is to predict the hospitalizations, right? So there is some mismatch. So the data-driven problem, approaches, have some advantages there.
Okay, because I'm a little bit curious, for example, probably you'll touch it because you have not gone into the COVID. So in the COVID-19 case, for example, the different type of mutations or variants will make an influence, and also depending on the policy that the local governments make, it will affect, for example, the mobility of the people. Okay, so these type of things come into the mechanistic model. So how does these things are captured?
Actually it's very hard to design a mechanistic model, right, which takes the government policy into account, which takes features into account, which takes mobility into account, which takes mask mandate into account, because you have to explicitly model, right, mathematical equations which take these things into account. So that's very hard to do, So basically our idea is that if you could get, the sets of features which capture these things, can you, basically make data-driven approaches which can, ingest all of these features together. Right? So there are some of these data assimilation methods which try to use weather, for COVID-19 forecasting, which try to use, lockdown mechanisms for COVID-19. But you have to basically, it's very hard to model everything together. Right? So there are some still some open challenges in designing mechanistic process.
Yeah, I agree. But these methods, they rely on the history.
Yes.
And they cannot consider the curveballs which are thrown to you. So I'm just.
Well, the hope is that the features that you have, right? Mm-hmm. So when we talk to COVID, I'm going to talk about what kind of features we use. The hope is that they are representative enough, right? So they basically, if you use mobility patterns, right, as your feature, if you use line lists, if you use crowdsourced syndromic surveillance. If you use these things as features, hopefully, you can learn a mapping from these features, which are informative, and then use them to predict, whatever it's you're trying to predict.
Okay, a small question. So from a kind of fundamental point of view, independent, so these methods, so for example, the infectious method is more a kind of linear type of model. It's not that much non-linear. It doesn't have it doesn't have this chaotic behavior. So can this method also apply to systems which they show very drastic,
yes,
non-linear type of behaviors?
Yep, I'll show that. Our method, I would not say linear, right, and non-linear, because these mechanistic processes are basically a set of ODEs, right, which are inherently non-linear, but they tend to produce smooth curves. And our methods, so there are these weekly cycles in reporting, right? So weekly patterns which are effectively bursty, right? And our methods can capture those really well. So I'll get to that. Okay, so let's move on. So basically, the first question is, why do you even, want to forecast ILI in presence of COVID, right? So the first thing to note here is that, so COVID ILI represents the burden to the hospitals, right? Whether the patient is visiting due to COVID or influenza, it's the patient is visiting a hospital, so you have to be prepared for that. And it can also be used, to help with indirect COVID surveillance, right? Especially in the early stages of the pandemic. So there was no, COVID surveillance mechanism, right? So nobody knew how to, get the actual estimate of how much COVID was out there, because the surveillance mechanisms were not established at all. And at such time, right, when there is an emerging infectious disease outbreak, these things could be very helpful. And it can also help disambiguate the trends between established trends and new evolving trends. So there were some challenges, right, in designing this method. So first one is that, historical data alone, basically the WILI values that you have seen in the past, is not good enough in the current scenario, right? Because this new trend, you have never observed it in the past. So the traditional ILI models were not able to adapt, right? So again, here, this is the new curve that you are seeing, right? And these are all the, historical ILI-based methods, both data-driven and mechanistic processes. And, they all are assuming that the curve is going to, predicting that the curve is going to go down, right? But this is the new trend, the uptick that we saw. And none of them were able to predict it. So basically what we, our idea was to, use these COVID-related signals, right? Ranging from mobilities, to tests and so on, whatever we could get at the time. And what we noticed was that these were, well correlated with this new uptick that we're seeing in the ILI values. So how do you, basically combine these two things, right? Your historical WILI values and the current, these new signals that you are seeing to forecast the new trends that in your data. So what are some of the COVID-related signals, to answer your question, right? So first things were line lists. So line lists, basically, so in the beginning of the pandemic, we had, these, so there were these contract tracing efforts, right? And we had some data on, how many cases were there in different regions, who had contacted with whom, and these were captured in the line lists. We had some data for testing, right? What were the number of tests administered? What was the positive rate? What was the negative rate? And so on. There were also some crowdsourced data signals like, digital thermometers at home collected from, Kinsa. Mobility, so Google and Facebook, they started releasing their mobility data when COVID-19 pandemic started, right? So we could use that because, after all, the disease spreads when people meet, right? It's like people-to-people transmission. So mobility plays a very big role there. We also had some exposures and social media survey. So basically survey is like, syndromic surveillance done by Facebook, and it's also openly available. So, so these were the data sets, COVID-related signals that we were trying to ingest. And, now, remember, the goal is to still predict these WILI values, right? So the historical model is still useful. So what we wanted to do was design a structured knowledge transfer from historical ILI model to this spatiotemporal COVID ILI model, right? And the basic idea is to steer, a Epidemic model that we saw earlier, with the new COVID-related signals, right? So we have these two independent models. The first one is the Epidemic model that we talked, slight modification of the model that we talked earlier. And the second one is, these COVID signals-based models, right? Which basically tries to learn spatiotemporal representations for all the reasons at the same time. So now the big picture idea here is to basically learn the embeddings, right? We saw that Epidemic gives you an embedding of the snippets, right? And so what we wanted to do was, take all these signals for all the reasons, right? And basically, learn a mapper, right? Which embeds the embeddings learned from, these COVID-related signals in the same space as the one given by the Epidemic, right? So if you have these two in the same space, then what you can do is you can impose certain losses on top of each other, right? You can say, hey, I want these two things to be similar, make them similar, right? You can basically impose these constraints on your neural network. You can also, define imitation losses. When the traditional model is doing well, you can say, I want my new predictions to be very similar to what you have, right? You can impose these constraints. So let's look at this, COVID augmented exogenous model at detail, right? So this is a global model with joint modeling of data from all regions. So we have 11 regions in total, 10 HHS regions and the national region. And we are basically learning a region-specific embeddings, right? And we also have a Laplacian regularizer. It's basically saying neighboring regions should have similar embeddings, right? So which are, in terms of their geographical proximity. And On top of that, we have recurrent architecture to basically model the temporal evolution, right? So you want to have a temporal consistency in some sense between your embeddings, and to ensure that we just use a recurrent architecture. So now let's look at the loss, right? The way we train these two models at the same time, right? So the way you train this model individually is exactly the same, as in general learning paradigm, right? So here I'm going to highlight the actual knowledge transfer part. So, we basically minimize this knowledge distillation loss, and it has two parts. The first one is called imitation loss. So here what you are saying is that minimize the difference between the predictions made by these two models, right? When these conditions, imposed by phi I holds. And phi I is basically trying to capture the difference between the prediction made by your original model and the ground truth, right? When this value is small, that is when your original model is doing well, give high weight to this loss, right? Basically it's saying make your new model as similar to the old model when the old model is doing well, right? And the exact same thing here. So this is in the embedding space. It's saying when the old model is doing well, make the embeddings that are learned by the old model and the new model as similar as possible as you can, right? So that's how we actually train this model. So now let's look at some of the results, right? So what we see here is that when APDP is not doing well, right, CaliNet can still do well, right? So this model can still do well when an APDP is not doing well. Now remember, APDP is designed to train, this traditional WLI values, right? And it has never seen, this uptick. So it can't work well when the values go up, right? Even when that happens, because we allow this flexibility and use COVID-related signals, this model is able to predict those things. And as we saw, there was a nice correlation between these COVID-related signals and the uptrend, right? So it's able to exploit that. On the other hand, when the values go down, right? So now APDP knows that, it has been saying for 3-4 weeks, the value has to go down. It's already April, right? That's what it's saying, because that's what it has seen in the historical seasons. And when that happens, there is actually a knowledge transfer, right? So when WLI values are low, CaliNet also has low values. So now, we are worried, right, that, does this emphasis on, adaptation, you are basically trying to adapt, steer the historical model. If you do that, you may get a good performance in this unobserved trend, but, is the overall performance compromised, right? So that was the worry that we had. And, we designed an experiment. What we did was, we tried to forecast the entire season. And out of 11 regions, right, we basically measured in how many of the regions our method was the best. And as shown here, CaliNet had the best performance in 5 out of 11 regions, and one of the baseline delta density. It's also a method that's being, that participates in the CDC challenge regularly. It had best performance in 5 of the other regions, and Sarima had overall 1 performance. So, it seemed like, we were very happy at the time, right? And it seems like we were able to predict, this uptrend in unobserved WLI values, even, just using some signals. But, COVID just started surging at the time, right? And, there were these lockdowns being imposed in New York City, and, nobody was, worried about COVID ILI values anymore. And, the question was, how do we actually forecast COVID-19 incidents in hospitals, right? So the questions changed at the time. And, we had this, new challenge coming up, which was basically the COVID-19 forecasting hub. So basically, we came up with this operational framework, right, which has a very simple neural model. And it had 3 separate modules. The data module, right, which basically deals with data pre-processing and collection steps. Prediction module, which basically gives the prediction. And explainability module, right, where we did post-processing and try to do a feature importance and so on. And it sort of worked like feedback to the data module, right? If you do feature importance, you can basically say this feature is more informative, and you can use this to improve your model. So the question is, why is this framework meaningful, right? So a thing that we notice is that by having a data module, right, and the prediction module separately, we can separate the noisy data from the learning process, right? Because, this is when, we're designing this forecasting framework as COVID was starting, right? Nobody had seen this disease at the time, and you were trying to forecast that something that you had never dealt with, right? So the data that we were getting were very, very noisy at the time. And it was a good idea, I believe, to decouple these things, right? Your data, like a pre-processing and data process steps, and your like a prediction module. And on the other hand, explainability, is a challenge for data-driven models. And if you are trying to forecast models, it's a must, right? So if it's like I'm not sure how important. So for all the tasks, interpretability is very, very important, but it's even more important when it comes to health-related things. And the explainability module, helps us, and it basically allows us to understand and connect forecasts with the epidemiological reasons, right? It says, okay, it seems like we can understand that, like how the disease spreads. So it spreads via people to people. If people are moving, a lot, then probably the disease will go up. So mobility is an important signal, right? So it allows us to basically, explore these things. So let's look at some of the challenges that we had, right? So in the beginning, it was like a lot of work just to, address these data challenges. So the first challenge was that, we had multiple data sources from multiple formats, and the formats, used to vary from time to time. You had a CS, and, you can't do this, you can't basically write different code each week, right? If you want to automate these things, you have to basically, have everything in place, so you can just click a button and everything happens, right? But it was very hard to do that because, the formats would just change, right? Your sources would, change the format, change the meaning of the data. So you had to, redo these things over and over again. And the next thing was, we had to select signals which had epidemiological significance, right? So, if you are trying to predict COVID, you better take the input, basically your input better be, capture the features which are meaningful, right? And so the next challenge was with temporal misalignment, right? So some of the signals had a lag of 2 weeks, some of the signals had a lag of 4 weeks, right? Some of them were delayed by 2 weeks, some of them had, spatial resolutions of one number per 2 weeks, other had one number for each day, right? So you had to basically do imputation to, get them all in the same units. Same thing with spatial misalignment, right? Some data were released at national level, other were released at state and even county level, right? So how do you impute them so that you get all of them at the same level? Now this is important because you want to build a model at a national level as well as at the regional level, right? So basically you want to predict what happens in each of the state. So these were some things that had to be dealt with. And so an interesting thing is that hospitalizations was one of the targets that we were trying to predict, right? And that CDC was interested in, but a lot of the states were not reporting that at all, right? So you had to be smart and try to guess what the ground truth is and then try to use that in your prediction. So there were some challenges with the prediction, designing the prediction module itself, right? Now you have very limited data, so you can't build models like I talked earlier, right? These deep neural network with thousands of parameters. It's inherently not possible. So we had to design a small neural network, right, with limited number of parameters. And we also wanted robust point and probabilistic forecasting, right? So for COVID, just predicting one number is not probably enough, right? You wanted to give a probabilistic range. So how do we do that? And basically, the way we solved this was by designing, a bootstrapping samples, right, and training a model in each bootstrap, and then you have a multiple forecast, and then you aggregated them to generate probabilistic forecast, right? So this is what the overall model, the prediction model actually looks like. So we had this, input data, right, that we started with, and then we basically bootstrapped and created a multiple samples from it. Trained a neural model on each of the bootstrap, so you get multiple probability, you get multiple point forecast, and you can basically convert that into a probabilistic forecast. Now, so that's for the first week, right? What's going to happen a week after the current week? You also want to predict what happens 2 weeks from now, right? And you don't have a lot of data. So what we did was we basically took this forecast, right, made it part of the training data, right, and then repeated the same process, and that gave you the a prediction for 2 weeks from now. So remember, in your predictions, right, you want to have some temporal consistency, right? And you can't train them by deep neural models which are designed to do that, like LSTMs and GRUs and so on, because you don't have enough data, right? So how do you do that? And basically, this was our idea, to tackle that problem. So let's talk about the explainability module, right? So we basically, and I have already talked about why we need them, right? And here we basically had a data ablation system, right? Which data ablation is basically you remove one signal at a time to characterize its importance, and it helps us evaluate signals which impact the predictions the most, right? And it helps us to basically draw insights in real time and also in retrospective. So again, there were some challenges in designing this, right? So this is like very interesting time, because you heard about COVID 3 weeks ago, you are stuck in your home, right? You had to defend your PhD and you have not been to campus, in like a month, and you were trying to forecast this, right? So we are understanding what the disease was, at the same time trying to forecast it, right? And trying to understand, what's really important in solving this problem. So the first challenge was, generating real-time insights of forecasts for the decision-making and communication. And, we did that by doing data ablation for the current week, for the week of the prediction, and also used an interface to visualize the signals, right? And their predictive contributions. If you have these things, if these things are visual, you can, it helps you, your intuition, right? In some sense, and, leads you to basically, make decisions. And we also tried to retrospectively understand the signal strengths, right? It's not just that, how important is this method in my current week's prediction, not just that, but, this signal was this important, in last week's prediction. The last week's real number just came in, and I made mistake of this much, right? So, it also helps you gain retrospective signal strength understanding. So this is what the interface look like, right? To basically both to do retrospective analysis and real-time analysis, right? Real-time analysis just helps you understand how important a signal is for the current week, and retrospective analysis helps you to basically gaze, there you can take your performance metrics into account, right? Because at that time the ground truth values would have been released, and you can basically use those. So let's look at some of the results, right? And these were submitted in real time to CDC. Right? So basically this is for California, and we're at epidemic week 23, right? At that time, this red curve, which eventually happened, was not observed, right? And these blue dots were our point forecasting, and this shaded blue region was our probabilistic forecasting, right? As you can see, we are not very confident about our predictions, right? Because at that time everything was still open. But if you look at the point forecasts, right, it actually captures the trend of what's actually going to happen, right? It says that the curves will go up and come down for a little bit, stay stagnant, and then go up, right? And this is actually what happened. Another example, again in California, right? So here we are saying the model is predicting the curves will eventually go up, and the red dots actually happened in future, right? So this was submitted a priori to CDC, right? And so again, getting back to your question, right? So this is here you can see in hospitalization there is this weekly pattern, right? So in Sundays and Saturdays, the reporting number goes down, and from Monday to Friday it stabilizes, and there is this underlying trend, right? If the cases are going up, all the numbers are going up, but there is this an inherent cyclic pattern. And so here this is the prediction made by our model, right? As you can see, this pattern is captured very well. So let's look at the numbers, right? So when you actually compare against other methods, how do our method does? So here the baseline is COVID hub ensemble. So there are about 12 to 13 models, including one from Iowa State, which submit to COVID-19 hub every week. And so there is an ensemble made by UMass and CDC, and we basically compare against that model. Right? So as you can see, for the national model, right, for both this is for point prediction and this is for probabilistic prediction, our method is, for the point prediction, our method is actually better for both week and for second week, right? This is a small gap, but still slightly better. And here, 1 week prediction, we are slightly lower, but 2 week predictions were slightly better, right? So overall, we were doing slightly better than the COVID hub ensemble. And so we then, we did 2 experiments, right? So first thing is, if you take longer weeks, 1 to 4 instead of just 1 and 2 weeks, does the performance, is still good? And if you look at the states, how does the performance look like? And the same thing happened here, right? So in US, we're still the better, But for some of the states, like our method actually worsened a bit. And when we try to, use our explainability model to, basically try to understand what's going on, we basically realized that the states, where there were data quality issues, we were basically suffering there, right? Because our model was, just plainly data driven, right? So there was no mechanistic processes. So this is like a garbage in, garbage out kind of situation, right? If the data quality is not good, then, the forecasts are also not good. So this is, like external evaluation of our method. We have been submitting to CDC for like last 2 years, and this is a paper, that's again written by folks at Iowa State, and they basically compared all these forecasts submitted to CDC, right? And our method was, ranked in top 5 out of 25 models. So let me talk briefly about, what's next, right? So there are some open problems, including data revisions. The next thing is working with sparse data, right? So, and this, marries between mechanistic and statistical approaches, right? So you have these SIR processes and you have this neural network. How do you marry? Like how do you basically design a model which look at both of these together? And one idea is to, basically impose the gradients, right? SIR equations are basically differential equations, and you have gradients, for your neural networks, right? You can basically match them. And so we tried to do that, and we got moderate success, and we have submitted a manuscript on exactly this topic. So I'm also very interested in microscopic forecasting, right? So you can forecast what happens at a national region, but within a microscopic environment, like within a given hospital, how do you basically characterize what's going to happen in next week, 2 weeks from now, and so on, right? That could also be actionable. Finally, would like to thank all of my collaborators, right, and CDC and COVID-19 Forecast Hub. Thank you very much.
So I'm curious about the COVID part of your presentation here. How much would or could sort of learning from previous COVID-like pandemics have helped or not the stuff that you're doing? Now, I guess that would depend on how good the data was when these events happened. So I'm not sure.
Yeah, so that's the trouble here, right? I mean, if we had like a COVID-like outbreaks, maybe you can say, like the SARS was a COVID-like outbreak, but we don't have a reliable, like a time series data and other related. So it's not just the time series, right? You need to have a mobility at the time, you need to have the tests at the time, and so on. So these things were not available. If we had that would have made our life a lot more easier, because that would have given us a very good starting point, right?
Thank you, Professor, for the presentation. I have a question about the noise you mentioned. I think the LSTM in a time series data is very likely to learn the noisy, and which means like fail. So what's the technique you use to remove the noise of the data?
Yep, so that's, again, a very good question, right? So for the COVID model, when we designed it, we really didn't have enough data to even think about using LSTMs, right? So, but even there, we're doing some imputations, right? Aggregations to basically, smooth out the data such that the impact of the noise would be reduced as much. But, for the KIM model where we use LSTMs, right, we had other regularizers. We used, this Laplacian regularizer, right? So if you have a noise in one of the regions, but you are saying, the embedding of this region should be similar to the neighboring regions where, there are no noises, then, the noise in the current region is reduced to some extent, right? So by, adding, so we had like, a very good pre-processing step for COVID-19 models, right? And for the previous models, we had some auxiliary losses, which tried to, combat noise to some extent.
All right, thank you. I have another question. Like, I think I'm just curious about the sample size. You mentioned you use about 20 years. And also a KNN model to clustering the season, which is similar to current season. Is it like the data, the input data is large enough so that you can learn? Because like if you have only a very small sample size, and after the clustering, you have a very small sample size, very easy to Like you just learn the historical data may be actually misleading because that.
Yeah, so so that's still an open question, right? So if we were just using LSTMs at that point, that would not have been good at all. But the clustering actually helped us a lot out there, right? So in the clustering, there is you are just trying to group seasons together, right, based on their historical patterns. So we didn't, so the number of data points that we had, right, it's 20 for 11 reasons, right? So you have 240 time series, in total, and those were enough for this model. So that's just based on experience for this particular task, right? So I'm not claiming that 240 time series is going to be enough for all tasks in the world. Okay, thank you very much.
Thank you, Vijay. You packed a lot of material in a 50-minute talk. Thanks a lot. So the final talk will be given by Professor Alexander Poleczek. He is Professor of Computer Science here at University of Northern Iowa. He is very well known in the area of protein sequence analysis and drug discovery. And his main goal is to study mathematical and statistical laws that underpin biochemical processes. So truly, truly multidisciplinary. So I would request Alex to come and give it.
I'll get yours up here. You are number 4. Yep. Oh, not that one. That one. If you want to use that, right goes forward.
Well, thank you very much for the nice introduction, and thank you to the organizers and sponsors of this really unique event at UNI. I'm thrilled to be among the 4 speakers here. So, as the title of my talk partially suggests, I will be talking about a particular machine learning method, namely matrix factorization, but in the context of a non-conventional geometry that underpins the space of the objects of interest. Current and past research in machine learning has mostly focused on the development and applications of advanced statistical and numerical optimization tools, such as classification, regression, sampling, shrinkage, and gradient descent, including methods such as AdaGrad, AdaDelta, as well as deep learning models, some of which we've seen today, long short-term memory, variational autoencoders, and so on. Disproportionately less attention has been devoted to studying the geometry that underpins the space of objects of interest. What do I mean by this? Well, most machine learning objects, machine learning methods represent objects of interest as points in the Euclidean space, in the traditional classical Euclidean space that we are all fairly familiar with.
for instance, in the setting of predicting user preferences to movies, a machine learning method would typically represent users and movies as points in the Euclidean space of certain dimension, and most of the time the dimension is huge. It's measured in the order of hundreds or even thousands. Here, in this illustrative toy example, I'm using dimension of 2, two-dimensional Euclidean space. And just to remind you, in the Euclidean space, the distance between two objects is defined as the square root of the sum of the squares of differences between the individual coordinates. And the shortest path between two objects is simply the straight line joining them. Aside from its key role in relationship inference, latent space is also critical in all downstream machine learning tasks, such as classification, clustering, data visualization, and in overall understanding of the function and dynamics of the system of interest. Recent years, however, have seen the development of theoretical methods that claim that all complex systems, including biological systems and others, exhibit hierarchical topology characterized by high degree of clustering. Embedding those systems in the Euclidean space is faced with challenges. So let me give you an example. Imagine trying to draw a hierarchical structure, a tree like this, on a piece of paper, like simulating embedding this particular tree into a two-dimensional Euclidean space. Well, most of us who have tried to do this realize that we soon run out of space unless we distort the proximity of these objects, unless we bring many of these objects together. And that's the problem in machine learning. So modern machine learning tries to accommodate these hierarchical structures still into the Euclidean space by adding dimensions to provide more room. So as I mentioned earlier, many of these modern machine learning methods utilize hundreds or even thousands of dimensions for this particular reason, not to distort the proximity between objects in the latent space. Another difficulty with using Euclidean geometry is that Euclidean distance metric satisfies the so-called triangle inequality. Specifically, the length of each size of a triangle doesn't exceed the sum of the lengths of the other two sides. And therefore, if 2 points in the Euclidean space are both close to a third point, then those 2 points have to be close to one another. This is a big problem in machine learning because, for instance, in the setting of user preferences to movies, we can have these two users at the bottom. The first one prefers romance and drama, and the second one thriller and horror. And obviously, both of these users are close, to some extent, to this user on the top, which prefers drama and thriller, because these two users share preferences to drama, these two users share preferences to thriller. So we do need to put them, both of these users, close in space at a small distance from the top guy, but at the same time, they have nothing to do, their preferences have nothing to do with one another. We have to separate them in space. And Euclidean geometry doesn't allow for Due to the difficulties I've just presented and some other, recent years have witnessed the development of machine learning methods that utilize non-Euclidean geometry to model the latent space. One of those geometries is the hyperbolic space. In the hyperbolic space, the distance between 2 points that are away from the center, from the origin of the space, the shortest path between any two such objects is almost the path through the origin. This resembles distance function on the trees, on these hierarchical structures, where the shortest path between two randomly selected nodes in the tree is almost the path through the root. A good biological analog is a phylogenetic tree, where the distance between any two organisms, where the shortest path between any two organisms is almost the path through the most ancient ancestor. Hyperbolic geometry, in contrast to Euclidean geometry, can accommodate the exponential growth in the number of these tree-like structures. The reason is that unlike Euclidean space, in which the circle circumference and the disk area are linear and quadratic functions of the radius, so a small increase in the radius results in a relatively small to moderate increase in the circumference and the disk area. In the hyperbolic space, the circumference and the disk area are exponential functions of the radius. So a small increase in the radius in hyperbolic space results in a very large increase in the circumference and the disk area. And that's the reason why hyperbolic space, and I show you here one model of the hyperbolic space called Poincaré model. That's the reason why hyperbolic space can easily swallow these exploding structures. In our research, we use a different model of the hyperbolic space. So there are several different but equivalent models of hyperbolic space, and I already mentioned one on the previous slide, the Poincaré disk. We use the so-called hyperboloid model of the hyperbolic space. And the reason is that this model, in our experience, allows for efficient gradient descent procedure, and it doesn't suffer from numerical instability, like Poincaré disk model. So in the hyperboloid model of the hyperbolic space simply can be seen as one sheet of a two-sheeted hyperboloid, which can be thought of as a sphere of radius square root of -1, the imaginary constant. Because simply the hyperbolic space is the set of all points in the ambient space with the property that the inner product of those points with itself, the hyperbolic inner product, is equal to -1. This is the equation of the hyperboloid. The inner product in the hyperbolic space somewhat resembles the inner product in the Euclidean space, except that the product of the last two components comes with a negative sign. So as I mentioned, this model is equivalent to Poincaré disk, but it's better for computing tasks because it doesn't suffer this numerical instability. They are simply equivalent. If we project this hyperboloid to the plane, to the xy plane, we will simply get Poincaré disk. Also, in the hyperboloid model of the hyperbolic space, the shortest path between 2 points is again almost the path through the vertex. And it's precisely, I'm talking about this white path, the shortest path between two objects, and it's precisely the intersection of the hyperboloid with the plane, here in blue, that passes through those 2 points and the origin of the ambient space. In the remainder of my talk, I will reintroduce the method of Euclidean matrix factorization, well-known method of Euclidean matrix factorization, and then I will talk about our own method for hyperbolic matrix factorization. But even though the setting of predicting user preferences to movies is good as an introductory toy example, I should point out that matrix factorization is applicable to many different tasks, in particular in biology and elsewhere. For instance, to the task of predicting drug-protein interactions, or drug disease associations, or drug side effects, predicting side effects for drugs, disease symptoms, and many other relationships and associations and interactions between biological entities. So, and I will also talk about the comparison, at least in accuracy, between Euclidean and hyperbolic matrix factorization. So, predicting drug-target interactions, which is the example that I'm going to use, although this technique generalizes to many different settings. Predicting drug-target interactions is a one-class classification problem. Basically, the input is a matrix of known, experimentally verified interactions, and we label those 1, so this is binary matrix, and 0 stands for everything else. No interactions or simply unknown. So in one-class classification problems, the task is to turn some of these zeros to ones, or perhaps more precisely, to turn them to numbers between zeros and ones, denoting the probabilities of interactions. So again, all in all, matrix factorization, just like the other machine learning methods, would try to position these objects, drugs and proteins in this particular case, into the latent space in a way that the proximities of those objects best explain the input. And that's how the predictions will surface out. Now, matrix factorization is known to outperform deep learning in recommender systems task, but it requires one assumption to work well. And that assumption, talking about drug interaction predictions, is basically that the space of all possible interactions is not too wide. It's not random-like. In other words, there are only a handful of properties of drugs and proteins that drive the interactions between drugs and targets. So going back to our example of user preferences to movies, this assumption would say that we don't have so many different users. There is a handful of typical users, maybe 100 or so, who knows, but every other user has the preferences either the same to this set of users, to one of those users, or his or her preferences are some simple combination of the preferences of this representative set of users. So the space is not too wide. Now, the good news is that this assumption has never been challenged in science. So in biology in particular, biologists agree that, for instance, drug-target interactions are mainly driven by drug substructures, and there are only finitely many drug substructures. And the same for side effect prediction, probably the same for user movie or user song interactions and so on. Mathematicians would call this assumption low rank. So they would simply say the matrix, when recovered, the complete matrix, the true matrix, not the input one, but the complete one, has a small rank. And mathematicians know that whenever a matrix has a small rank, I'm not talking about the input, but the output matrix, the recovered matrix. Whenever it has a small rank, it can be represented as a product of two lower dimensional matrices. So if the recovered matrix, not the input one, has m drugs and n proteins, then that matrix can be represented as a product of two lower dimensional matrices. The first one having m columns and k, m rows and k columns, and the second one n rows and k columns, where k is much smaller than either one of these two dimensions. Over time, matrix factorization techniques became, within the last decade, quite sophisticated. So here, I'm actually presenting what we call logistic matrix factorization. It models the likelihood of an interaction not simply as a dot product of the latent vectors, but using logistic probability. Exponent of the dot product divided by 1 plus exponent. That's what logistic matrix factorization, there is a consensus these days that logistic matrix factorization should be the method of choice rather than non-negative matrix factorization. So the probabilities are modeled this way, and again, our task is to try to approximate this input matrix using two matrices of latent preferences, and when we combine them this way, these two matrices, we're gonna get the final probabilities. Now, Euclidean matrix factorization, in particular logistic one, will derive these probabilities through Bayesian inference, where these priors are Gaussian distributions. And the final loss function looks kind of nasty, in particular because here, aside from known interactions, I also included the so-called side information. So oftentimes, people use things like pairwise similarities of drugs and pairwise similarities of proteins to enhance the prediction accuracy. And this is very reasonable because it's a fact that similar drugs bind similar proteins and vice versa. So this can only improve the accuracy. And this is actually built into this expression here. So we want the latent vectors for drug I and drug J be as similar as those two drugs are similar. So when we minimize this, we're going to achieve that effect. Latent vectors of similar drugs will be similar. So this setting will enhance that idea. So keep in mind, here I'm talking about Euclidean matrix factorization. I'm using, in this loss function, Euclidean inner product or Euclidean dot product. And you're guessing what's coming. What we did, don't get me wrong, people have been using non-Euclidean latent spaces before in the context of deep learning and other machine learning techniques, but not in the context of matrix factorization. So what we did, we simply replaced the Euclidean dot product that was here by the negative squared Lorentzian distance, which is hyperbolic dot product between x minus y and x minus y. And now I'm gonna refresh your memory when it comes to that problematic triangle inequality. this squared Lorentzian distance doesn't satisfy the triangle inequality. It satisfies all properties of a distance matrix, namely non-negative, is zero if and only if 2 points are the same and so on, but it doesn't satisfy the triangle inequality, which is a good thing here. We also derive the loss function through Bayesian inference. However, we cannot use Gaussian distribution here because we are talking about a hyperboloid rather than Euclidean space. What we use here is prior work by a third party that defines the so-called pseudo-hyperbolic Gaussian distribution. I'm not going to go into any details. I'm just going to show you here an example of a Gaussian distribution in blue and samples from this pseudo-hyperbolic Gaussian distribution in red, of course, on the hyperboloid. So that's what we use as prior. So we disclose this in a provisional patent application and also in a publication, if I can call it, that sits on a preprint server. I can show you the reference later on. So now that we have our loss function, I didn't show you the form. It looks quite similar to the Euclidean one, but it uses Lorentzian distance in place of Euclidean inner product or Euclidean distance. Once we, now that we have our loss function, we can apply hyperbolic gradient descent, which is a bit trickier because if we compute gradient at a point on a hyperboloid, the gradient is not in the hyperboloid anymore. It's in the ambient space. So we have to project it back to the hyperbolic space. But that's the only difference. So actually, I should tell you about the requirement to apply gradient descent. The requirement is that if we have our loss function defined on the hyperboloid, in the hyperbolic space, in order for this function to be minimized by this procedure, it has to be also defined in the neighborhood of the hyperboloid, in the ambient space. And that's the case with our function. So we can go ahead and apply this three-step procedure. Basically, we first compute the gradient in the ambient space, and then project it to the hyperboloid via two projections. We first project it to the tangent space, and then via the so-called exponential map. Again, the details are on the preprint server. We project that tangent space vector back to hyperboloid. And that's how we perform this update step. So here is the accuracy comparison. We ran our accuracy benchmark on 7 different biological databases. The first 5 are databases of drug-target interactions. The next one is a comprehensive database of drug-disease associations. And the last one is the database of side effects. We use 2 popular classification metrics, the area under the precision recall and the area under receiver operating characteristics. And as you can see, hyperbolic matrix factorization consistently outperforms Euclidean matrix factorization in every benchmark and according to both of these widely used classification metrics. What's more interesting than this is the table at the bottom that shows that while exceeding the accuracy of Euclidean matrix factorization, hyperbolic matrix factorization actually at the same time lowers by an order of magnitude the dimension of the latent space. So to put it differently, for instance, for nuclear receptors database, we only need 5 numbers to describe every drug and 5 numbers to describe every protein to do better than the classical matrix factorization with hundreds of numbers, hundreds of descriptors. And this is good news when it comes to scalability of the model and time and space complexity and so on. So in the remainder of this presentation, I'm going to talk a little bit about some applications and directions to our future work. In our recent publication, we extended the utility of matrix factorization to repurpose the existing set of FDA-approved drugs. We call them compounds here. So basically what we did, we enhanced the existing relationships between drugs and diseases. That's called drug repurposing, as you know. So to do this, we first utilized a public resource, a network, a biological network called HETIONET, which is compiled using 29 public databases between the individual domains. And all in all, this is a large network. It contains 50,000 of different nodes, tens of thousands of genes, and 1,500 drugs, and about 400 diseases, and so on, for a total of 50,000 nodes, and more than 2 million edges between these nodes of 24 different types. So if you count these arrows, there are 24 of them, okay? So, for instance, there are edges of the type compound upregulates a gene, or disease associates gene, or gene expresses anatomy, or compound causes a side effect, or disease presents a symptom, and so on. So there are 24 of these edge types. Of course, these are all meta edges and meta nodes. They hide many of them inside, right? So all in all, enormous size, very sparse network. So what we did, we were focusing on enriching this particular meta edge, compound treats disease, on repurposing the existing set of FDA-approved drugs. And of course, one way to do that is just to apply matrix factorization on this matrix, compound treats disease, and go from there. But we went a step further. We basically first enhanced this network, this sparse network. We applied matrix factorization to each one of these meta edges to basically arrive at a very rich but probabilistic network in which, for instance, every drug can treat every disease, but with certain probability. Okay, and mostly those probabilities are very close to zero, and oftentimes they are very close to 1. But it's a probabilistic network. And then in that probabilistic network, again, you know, one can assess the probability that any drug can treat any given disease by just looking at the corresponding probability that we computed using matrix factorization on that particular edge. But aside from that particular edge, we looked at all possible paths through the network to go from compounds to diseases. So again, one of those paths is the direct path, and we have that probability, but we are also interested in the probability of the type certain compounds upregulate certain gene, which is downregulated by that particular disease, and so on. So there are so many different paths. So what we did, we ran cross-validation to compute the informativeness of all of these paths, and then we identify 10 most informative paths, 10 paths most supportive of drug efficacy. So here you see the direct path, but you also see compound binds gene, associates disease, compound binds gene, expresses anatomy, localizes disease, and so on and so forth. So with these 10 paths,
we computed the weighted sum of these, and we trained weights also. It's not so simple process. So in the end, we arrived at this algorithm, which we call EONet. Eon in Greek means life. This integrative approach where we combine the probabilities along all of these supportive paths and compute the weighted sum, and then we computed the accuracy, again using AUPR and AUC, of this integrative approach and compare it to the accuracy of the approach that follows any given path. It's most interesting to look at the top one because this is the direct path. This is what plain matrix factorization between compound domain and disease domain would do. So it will achieve these classification scores. Actually, here at the bottom in bold, we have the scores obtained by integrative approach, and we underline the best scores obtained along some of these 10 supportive paths. So as you can see, EONet significantly increases the accuracy of the individual paths. We deployed this algorithm to a web server running at UNI, at bioinfo.cs.uni.edu. And actually what we've done here, we've also used the same approach, the integrative approach, to enhance all other edges in the network, not only compound trees disease, but all other edges. So if you wanted to try this out, you can simply go to bioinfo.uni.edu, and you can issue some queries like this. So for instance, if you say, give me all compounds that treat Alzheimer's disease with that direct probability greater than 0.3, but at the same time, give me all genes that those compounds bind with probability greater than 0.1, and at the same time, those genes are associated with Alzheimer's disease, let's say with probability greater than 0.1, then you're going to get a response like this. For instance, donepezil is one of those drugs that treats Alzheimer's according to the direct edge with probability greater than 50%, and it also binds the gene CYP1A1 with probability 0.3, exceeds the input, and it's associated with Alzheimer's with probability of almost 0.4. So I'm mentioning this in case you're curious enough to visit this web server and to try out some queries. We published this work in IEEE Transactions of Computational Biology and Bioinformatics. Actually, it will be published in July. And of course, our intention is to repeat this study now that we have much more accurate but lighter matrix factorization method. We want to repeat this study with hyperbolic matrix factorization and just compare the numbers head to head. I didn't pause for questions, so I might have ended up my talk a bit earlier, which doesn't have to be necessarily bad. I do want to thank you for listening to my talk. And before I maybe take some questions, I do want to acknowledge my more than 2 decades collaborator, Professor Lei Ji from CUNY Graduate Center. His contributions are extremely valuable due to his training in both chemistry and machine learning. And then here are the references to our work that you can read if you're interested enough. So thank you again, and please, if you have any questions, fire them up.
Thanks for the great talk. I have a question about, so basically, can you give some insights on why the hyperboloid space, avoids these numerical issues? Because the operators, they look very similar to Euclidean space, right? So what is it so special about hyperboloid space, that makes it avoid numerical issues?
What is so special to avoid all of these issues, right?
Just the numerical issues.
I'm sorry?
Just the numerical issues. You said that there were no numerical issues, right?
Right. So the main two things, and I'm not quite sure if I'm directly addressing your problem, your question. So please let me know if I don't. But I mentioned two issues with Euclidean geometry that is a no issue with hyperbolic geometry. The first one is Euclidean space cannot accommodate hierarchical structures. And all of these structures, all of these systems that we talk about are hierarchical. They are simply exploding in the number of relevant features. In Euclidean space, it's just not spacious enough. The area of a disk is only quadratic function of the radius, whereas hyperbolic space is roomy. It can accept these exploding structures. So that's one issue. The other one is triangle inequality that is not desirable. However weird that sounds, it's not desirable in machine learning. I'm not sure if I'm. But you mentioned numerical issues. Well, I say we have more numerical issues than in Euclidean space. So for instance, when we compute the gradient, it tends to go aside from these time-like regions of vectors. It tends to go grow into a space vector, and we have to, in order to control the process, the minimization process, we have to often trim the gradient, bring it back, and then let it breathe a little bit more. But we have more numerical issues than Euclidean geometry does.
Oh, okay, great. Thank you. Maybe I misunderstood things, when you were talking about the numerical issues. Thanks.
But less than if we were using Poincaré disk. So I hope that's clear. That's the reason why we use hyperbolic space, because if we use Poincaré disk model, then just technically, we couldn't perform gradient descent due to this instability.
That makes sense. Thank you.
So, Alex, great talk. The first question I have was in the last slide that you showed there, where people can go to right. That's using Euclidean. So you haven't yet done your hyperbolic thing to this. Okay.
No, I had a student. I asked a student to try to repeat this process. It's just time consuming.
Okay.
You have these 29 different types of edges, and you have to perform gradient descent in hyperbolic space with all numerical, adjustments that you have to do. It's just time consuming. No, we haven't done it yet, but we are excited to look at the result.
The second question has to do with the geometric interpretation of the gradient in hyperbolic geometry. So in terms of, in Euclidean geometry, you can say, if I compute the gradient at this point, it represents, so it gives you a direction that is perpendicular to the surface. Do you get the same sort of thing perpendicular in the sense of hyperbolic geometry, or what? What does it mean?
Yes, exactly. So the interpretation of the gradient is the same. It gives you the direction of the steepest descent.
Yeah.
Okay, so that's the same. And then this orthogonality is also the same, although the notion of the angle
is
in
different.
Hyperbolic geometry is slightly different.
Yeah, okay.
Angle in hyperbolic geometry is inverse hyperbolic cosine of dot product divided by two norms, just like in Euclidean, but it's inverse hyperbolic cosine as opposed to inverse cosine. And then inside the inverse hyperbolic, you have an extra minus sign. So, but yes, orthogonality holds, yes.
Interesting. The other thing that I sort of, I guess it speaks to the comment you made about how your hyperbolic method sort of, in terms of preserving, I want to say preserving distances between things.
Yeah, you can
your
say that.
projection, you had one slide that is a projection from a hyperboloid down to the plane, which I thought seemed to demonstrate that pretty well, in the sense that where you had points scattered on the hyperboloid down on the projection, they also seem to reflect exactly the same sort of thing that you had on the.
Yes, because these are different but equivalent models. So some people are actually, in these tasks, some people are using Poincaré's, but they are equivalent. So this is just to show that they are equivalent. One projects in some kind of one-to-one and non-to fashion to another.
Great.
But yes, your observation about a hyperbolic space offering more room to place the objects of interest at a distance that can explain the input is completely correct, yes.
Well, actually, one more thing. You know, so I'm an analyst. So the triangle inequality is a very close friend of mine. So it is said that here it's actually a liability, right? You know, it's unclear to me why failure of the triangle inequality actually
a good thing.
Except for the way you explain the geometry with the relationships with the, that picture that you.
Yeah. So if triangle inequality would hold, then these two people would have to be placed close to one another in space, and that's exactly what you don't want, because they have totally different preferences to movies, right?
So here's one of the reasons I'm asking, Alex, is that in the LP spaces for sequences, right, finite sequences, so you're in n-dimensional space, and look at LP where P is between 0 and 1, strictly between 0 and 1. The triangle inequality fails. And I'm just curious what that would mean if you did not use, you know, if you were still in Euclidean space,
but using
P's which were strictly between 0 and 1.
Well, you know, this is still not exact science. It might be close to, it is close to pure mathematics, which is weird on its own way, because hyperbolic geometry is part of pure mathematics, and the definition of pure mathematics is it doesn't have any applications, right? Well, here you see a straightforward application. Now, so my point is, we don't know until we try. So this is still trial and error.
Right.
So we can try LP metric basically in Euclidean space, right? Not necessarily L2. I'm sorry for not necessarily L2, but we can try LP. You know, LP does satisfy triangle inequality. Actually, if you think about that, squared Euclidean distance, squared one,
right,
doesn't satisfy triangle inequality. But you know, hyperbolic space has another advantage over squared Euclidean, because still squared Euclidean cannot swallow these phylogenetic trees and social networks and different other systems.
So that's the way I see it.
Right,
Could be wrong, but
Right. No, it's great.
thank you.
Thank you, Alexander. Beautiful, very insightful talk. Thank you very much. And this brings us to the end of this symposium. I think we have all enjoyed the talks. Very illuminating, very informative. So let us thank the speakers once again. Thank you, and we are done for the day.